Thank you very much, Sabrina, and actually thank you very much for creating this very promising and interesting workshop. And I think this is cool. Yesterday the lectures were great. So and also I'm happy to I feel honored that I'm the first speaker of this workshop. So I try to be a bit more basic. So I'm going to talk about celestial amplitudes and asymptotic symmetries. And this is work I did together with Angelos Fotopoulos, Thomas Taylor, and Bin Zhu from Boston, and we also have some work with Wei Fan from China. So this was essentially a work we did last year on the asymptotic symmetries. And I also will mention some results from some older works with Thomas on these two works. So let me just, because I'm originally coming from amplitudes, let me recap what we are usually doing when we compute amplitudes. So when we have an n-point amplitude, we have n external momenta, we specify them, and then so we have this on-shell condition, and then we specify the amplitudes by asymptotic wave functions. So we use asymptotic wave functions usually which transform simply under space-time translation. That means in particular these amplitudes, they are manifestly translation invariant, and then the amplitudes describe transitions between momentum eigenstates. So that is the usual thing what you do in four-dimensional Minkowski space. But as I also want to show in my talk is that the four-dimensional Minkowski space is probably not the right space to see all symmetries of scattering amplitudes. And we will make use of the fact that scattering amplitudes in four-dimensional Minkowski space have some interpretation as two-dimensional Euclidean conformal correlators. So the basic idea is that rather than, so this is the simplest amplitude in four-dimensional Minkowski space you can imagine. It's a three-point scattering process with three external momenta, P1, P2, P3. And the basic idea is that we have some auxiliary two-dimensional space, which will be the celestial sphere, on which we map all these external states that become points. And there's a well-defined map how this works. And then we, in principle, we hope that we have some underlying conformal field theory on the celestial sphere, which allows us to compute this amplitude by the relevant conformal field theory. So, I mean, in a very simple terms, we hope that we get, or we should expect something like of this sort. So this is just dictated by conformal invariance on the celestial sphere. But as we will see in a moment, I mean, amplitudes, even the three-point amplitudes will be much more look much more involved. But this is the basic idea that we, rather than considering four-dimensional, I mean, space-time QFT correlators in four-dimensional Minkowski space, we go to a two-dimensional space as a celestial sphere, where then we compute with some CFT methods this two-dimensional Euclidean correlators. And the reason why this works is that one of the reasons is that the Lorentz symmetry in four dimensions is isomorphic to SL2C, which now becomes a on the celestial sphere SL2C transformation on these positions. So this is now a global conformal symmetry. So why should we leave the four-dimensional Minkowski space and compute amplitudes on the celestial sphere? Well, we will see that that we get some constraints. We want to constrain the S matrix and understand amplitude relations, which we don't understand well in four-dimensional Minkowski space. And we have also then a completely new way of looking and investigating new physical principles and mathematical structures to constrain the S matrix, and also note that now in this two-dimensional conformal field theory, our amplitudes are sensitive to both UV and IR physics. So this will lead to powerful constraints on the analytic structure of the amplitudes. So there might be a lot of powerful constraints and principles at hand once we have understood this celestial conformal field theory, which allow us to construct these amplitudes by first principles. And then this also gives us a completely new way of looking at quantum field theory and quantum gravity, which eventually should lead also to some flat space holography. So this is now was the motivation why we want to do this. And let me now go to a bit more in details. So what is the celestial sphere? How do you see it, or how do you get it? I mean, we start with the four-dimensional Minkowski space, and then we introduce retarded or advanced Bondi coordinates. So these are the retarded Bondi coordinates. So you introduce this coordinate, then the metric looks as follows, and then you see already that at constant u, so it's constant retarded time, you see this one-dimensional complex sphere with a certain radius. So in pictures, this emerges as follows. So just, I mean, here are the two diagrams. One is for the retarded and the other one for the advanced Bondi coordinates. So let's just look at this observer who sits here at r is equal to 0, and then he looks at the sky, and then he sees this two green dots. He sees light coming, arriving at a given time at his place. These two dots, that is what he sees. You can compute, this happens at constant advanced time v, so this is constant v. So if actually this v gives, this computes the time, how long it takes to arrive at his place. Of course, if he waits a little bit, then he sits here, then he will see the light which comes from here and from here. But actually, the observer here doesn't see only these two green dots, but he sees the whole two spheres, the celestial sphere, which is spanned by this C and Z bar coordinates. I mean, that is simply because of this four-dimensional space. But now in the retarded coordinates, though, then he looks in the future, then you can also draw these spheres here. And so at each point here, r is equal to 0, you have essentially two spheres, namely this sphere here and this sphere here. So that is, of course, a perfect setting for amplitudes, because this is now the arena for outstates, and this is the arena for instates. So this is exactly the situation you have for considering amplitudes. And so you have these two spheres, and they will serve as the target space where you in and out states are coming. Now, so there's this celestial sphere where massless particles exit or enter. I mean, there's a one-to-one correspondence. You can associate to each massless particle with a momentum. You can compute the point on the celestial sphere at which it enters or exits it. And since we have this conformal symmetry, I mean, we have some, I mean, the Lorentz quantum numbers turn into some conformal quantum, I mean, some quantum numbers, SL2C quantum numbers, I mean, which are the conformal weights h and h bar. So we can just compute this this point on the celestial sphere, or vice versa. We can determine we have a point on the celestial sphere, and then we can compute the momentum of a massless particle, which is associated to this point. So by introducing this auxiliary null vector q, which is given here, you can write down this momentum in this way, and this gives exactly the momentum of a massless particle which hits the celestial sphere at the position c. Of course, and omega is the energy. This is the zero component of this momentum. Of course, you can invert this map, and then you can, for a given four momentum, you compute the position, and then you on the celestial sphere. This is given by this formula. And so, in other words, when you start with a massless four momentum, which is on shell has three real parameters, you map them to this omega in this position, this complex position. So you map the total three real parameters to a total of 3 real parameters. So this will be the quantities omega, c, and z bar, which will enter our amplitudes and our wave function and everything what we need to need for computing physical quantities. So I have already emphasized at the beginning that we usually in 4-dimensional Minkowski space we talk about we implement manifest translation invariant, and then we scatter plane waves. But now, I mean, this we can simply compute it by inserting our coordinate transformation. Now, actually, we rather than having plane waves, we have boost eigenstates with respect to the retarded and advanced time. And now let me make an interesting remark. Of course, when we scatter n particles, and then we have n positions on the celestial sphere. So, I mean, in my talk, I will always only talk about massless particle scattering. So we have, for each of these n particles, we have its position on the celestial sphere. So we have these n points, which I have given you the formula. And now you can associate, I mean, usually in 4-dimensional space, you work with spinor helicity brackets when you compute amplitudes. So you have this England square bracket. You can directly compute or express them in terms of these coordinates on the celestial sphere, in particular the invariant, the kinematic invariance, the scalar product of the external momenta is given in terms of this formula. But now with this Pij scalar product, actually you can prove this formula. So you just plug in this Pij given in terms of Cij, and then you can prove this formula. These are n equations, and actually these equations, they are known as the so-called scattering equations. So that means your positions on the celestial sphere, which describes the scatterings, are exactly solve the scattering equations. And these scattering equations are also related to the so-called subtle point of equations in high energy string theory. I will come to them in a moment. So there is seems to be a nice link between the celestial sphere and solutions to the scattering equations, and also subtle point equations in high energy string theory. This is just now a side remark. So now we need to further set up the stage. So we have now this celestial sphere, where this momenta become positions on the celestial sphere. So we have this momenta now expressed in terms of c, position c and omega. This, recall this q was this null vector. And now, of course, we need operators. So we have now conformal primary wave functions phi, which need, of course, to have a proper transformation behavior under conformal transformations. Recall this conformal transformation is global transformation is global conformal transformation is accompanied by a Lorentz transformation in the 4-dimensional Minkowski space. So we expect this transformation property on this conformal primary wave function. And then we have this conformal weights, h and h bar. And of course, with the usual formula, they determine the spin and the dimension of this fields. Now, how do we get this conformal primary wave functions? In the massless case, we can obtain them by just performing a Mellin transform with respect to the energy omega. So here you have some states from the Minkowski space, which you rewrite in terms of your celestial coordinates, and then you do a Mellin transform, and then you get your conformal primary wave function. So let me just make an example. This is the plane wave, and then you do this Mellin transform. I mean, there's some regulator epsilon here, and then you get this object. So this is a conformal primary wave function on your celestial sphere. And you can, of course, also construct it by first principles, because this is a massless scalar field, so it has to solve the Klein-Gordon equations in 4 dimensions. And actually, by looking at solutions to the Klein-Gordon equation and And looking at the norm and for completeness conditions, you will find that this delta, this dimension, has to be lie on the so-called principal series, which is delta has to be 1 plus I lambda. So this is I is complex unit. And then since this is a scalar, you can immediately compute the conformal dimension of this spin 0 conformal primary wave function. Now, how do amplitudes look like? Of course, eventually we want to compute amplitude on the celestial sphere with our yet to find celestial conformal field theory. But actually, the strategy at the moment is that we take some well-known understood amplitudes from Minkowski space, transform them into the celestial sphere, investigate the properties to understand the physics on the celestial sphere better. So we start with an endpoint scattering amplitudes in the Minkowski space. So that's usually specified by external momenta p and polarization vectors epsilon. And there's a momentum conserving delta function. And then we have learned just before that our states we transform by Mellin transform from to conformal primary fields. Now we just perform a Mellin transform on this amplitude on this four-dimensional or this Minkowski amplitude. We first express everything in terms of celestial coordinates. So all these p and epsilons are expressed in terms of omegas and c's, coordinates on the celestial sphere. And then we do this n-fold Mellin transform. And then we get an object which depends on the celestial coordinates. So these are n c's and on these dimensions of each of these conformal primary operators. So that is now the amplitude which you these equal to 2 conformal field theory should compute by involving a conformal wave package and by the underlying methods of this yet to be found celestial conformal field theory. Let me just make a sample, show you a few simple amplitudes, namely the 4 gluon gauge amplitude and 4 graviton gauge amplitude, just to give you an idea how these amplitudes, how the celestial amplitudes look like. So this is the 4 gluon MHV amplitude. So it has you scatter it scatter 4 gluons, 2 with opposite helicity. So this they have minus helicity, and the other 2 have plus helicity. And then you get first, you might see, okay, this looks fine because this looks like what you expect from a conformal field theory 4-point amplitude. So that is this famous factor, which is the positions of the vertex operator Ci minus Cj, which now are positions on the celestial sphere. Also, you expect that the conformal Grosch ratio of a 4-point scattering amplitude enters. So this is a conformal Grosch ratio. Note now that since the Ci are related to the momenta, this is now an object which expresses or which is given in terms of kinematic invariance. In fact, you can express it in terms of the inverse scattering angle. So this is the scattering angle in the center of mass system of 4 particles. And that, of course, here tells you already that this conformal Grosch ratio has to be real. There's another argument that this conformal Grosch ratio have to be real, and namely that, by looking at 4 momenta, you see that they have to lie on a 2-dimensional subplane in the 4-dimensional space, and this 2-dimensional subplane crosses or intersects the celestial sphere at a circle, and this is just a condition that this 4 points lie on the circle, or it is just a reality condition for this scattering angle. Now you can check that this is indeed conformal invariant, so it's invariant under conformal transformations acting on these CIJs, and by that you can pick up what this conformal dimensions for this scattered clones are. Indeed, you can compute H1 minus H1 bar, that's -1, so this gives exactly the right spin and so forth. But also keep in mind that there's this delta function which tells us that that there's some condition on this spectrum of this conformal primary operators which we are scatter. I will come to this delta function, I mean, actually throughout my talk very often, so this play an important role. In fact, also higher point clone amplitudes have been computed. They have been computed by these people, and actually it's interesting because they involve some interesting structures, so that can be essentially given by integrals over certain hyperplane arrangements or Grassmannians. So there's some nice appearance of Grassmannians also when you go to higher points. Now, the graviton amplitude is, of course, very natural now to ask how does the 4 graviton amplitude look like? At first glance, it looks almost like the gluon amplitude, except, so again, there's this delta function constraining the Grosch ratio to be real. And then, so the main difference, I mean, actually, the main difference is this argument of the delta function. Now, so there's now this, instead of -4 here, there's a -2 here. And I will come to this, but this is now the 4 graviton amplitude. It's the 4 graviton amplitude now on the celestial sphere, so it's on the conformal basis, and it will be now play a very important role, this graviton amplitude, when we investigate asymptotic symmetries and by looking at soft graviton theorems. So we will perform some limits on individual gravitons, delta I go to 1 to 0 and so on, and this will be important limits for discussing symmetries and also finding symmetries. Of course, what is already also the case for the clone amplitudes, there is no holomorphic factorization into something like left movers and right movers, as you are known from closed string theory, and that is actually because of we will come to this because of the super translation operator. I mean, that's because it works, it acts in a different way. But of course, you see simply also this comes already by this delta function on the Grosch ratio, that there's no holomorphic, anti-holomorphic factorization. Now, for completeness, let me also show you what these amplitudes, the simplest string amplitudes look like. This is not because I want to do string theory now. It's actually more because I want to show you how these things change when you have an infinite tower of massive states in the game, or when you equivalently when you have an infinite series of higher derivative operators in the game. So what now you compute, we have computed it in type 1 superstring theory, though this is the 4 clone amplitude in type 1 superstring theory. And so you have, this is essentially the same expression, what is in blue, what you have for the field theory for clone amplitude. And there's only this alpha prime here, and then there's this so-called form factor, which is given here. So as usual, this form factor is an integral over the worldsheet position. I mean, now since the 4-particle scattering process, you can also on this string worldsheet, you can introduce a Grosch ratio, which is essentially given in terms of this x. So this is essentially an integral over the Grosch ratio on the string worldsheet. You can expand this integral now with respect to this Grosch ratio. So now we have 2 different Grosch ratios. We have the Grosch ratio R on the celestial sphere, and we have the Grosch ratio X on the string worldsheet, which is a priori on this slide no relation. So we can expand this in terms of inverse celestial Grosch ratio R, And then actually you get integrals which are Nielsen polylogs, and you can compute them, and they give some periods which are encoded in this multi-zeta values. So you get a power series expansion in the inverse cross ratio, and of course, the leading piece gives you just the classical contribution. So this is the leading piece, which was just the field theory computation, which was just this delta function constraining the dimensions of the conformal primary operators. Now, there are several remarks I want to make. That there's the alpha prime expansion is trivial now. So you see there, you might have asked yourself, why is it not an alpha prime expansion? There is no alpha prime except this overall factor. And that is, of course, must be the case because we have a conformal theory, so there's no room for dimension. So you can only have this alpha prime somewhere trivially entering. Instead, we have now an expansion in the small scattering angle, or in this inverse cross ratio. That means that so now alpha prime expansion is possible. So all heavy string modes, or I mean, if you have some other theory with heavy strings with heavy modes, so all heavy modes participate on the same footing, and there's no decoupling of massive states. You can only recover field theory, I mean, since there's no alpha prime, so you can only recover it in a different limit. Maybe you have to send this scattering angle theta to 0. In other words, you send r-1 to infinite, and then by that you kill all this coefficients of this power series. So that is a crucial difference. Now we want to ask the question. So we have now a string worldsheet, which is actually on which you have a nice conformal field theory, namely a free conformal field theory. And we have a yet to be found celestial conformal field theory. And of course, it would be nice if there would be some relations. And now we ask just the question, is there any relation, or at least in some region? And that actually we can find when we go to the so-called high energy limit in this conformal theory. So
there's one question, if you don't mind being interrupted during, or like.
Okay, yeah, I don't, yeah. So what is the question?
For her?
So isn't this so string theory is you'll define it either in 10 dimensions or 26 dimensions. So the celestial CFT for string amplitude, shouldn't that be a 24-dimensional CFT or 8-dimensional CFT? How would that be related to this 2D celestial 2D worldsheet that you're looking at here?
Well, this is a superstring amplitude in 4 dimensions. It's at 3 levels, so it doesn't matter whether you take the result in 4 dimensions or in 10 dimensions. So you have your scattering result from string theory in 4 dimensions, and then you ask the question, how does it look on the celestial sphere? So it's the same thing. What you only have, as I have said here, you only have an infinite tower of massive states in addition.
I see. Okay, thank you.
You're welcome. So now we want to see what is there some limit where we can where the string worldsheet becomes a celestial sphere, and recall there's this string form factor which is an integral over the cross ratio on the string worldsheet X, and you can consider this high energy limit that this sum of lambdas. Note that this lambdas enter the dimensions of your conformal operators, in that case of the clones. You can then this to infinite, and then you can perform a subtle point approximation, and then this form factor is a leading contribution at the subtle point, and so you compute it, and then the subtle point is given in terms of the celestial cross ratio R modulo SL2C transformation. So you see that in that limit, the string worldsheet position is now localized at the cross ratio on the celestial sphere. So in this limit, the vertex operators of your string vertex operators are equal to the positions of the momenta or the positions on the celestial sphere. So there's a one-to-one correspondence of worldsheet vertex operator positions and points on the celestial sphere. And as according to what I have shown you at the beginning, this is also equivalent then to the solutions of scattering equations. Then that means at this point, the celestial, in this limit, the celestial sphere is equal to the string world, and then in this regime, there's also the relation. It must be a relation between the conformal field theory on the celestial sphere and the free worldsheet CFT, which was the conformal field theory computing your string amplitudes. Let me just remark that in a recent paper by these people, they also have investigated this high energy limit, beta goes to infinite, in field theory, and so I'm looking forward actually to Nima's and Anna Maria's talk tomorrow. It will be, I think it will be partially about this beta goes to infinite limit. So now I have always talked about this yet to be found celestial conformal field theory, and we want now take our amplitudes and understand better this underlying conformal field theory. And of course, what you want first to understand, of course, among many other things, is operator product expansions. And I give you here just an example of an operator product expansion of two clone operators. So this is spin -1 and this is spin +1, and this is the gauge index A and B. So I mean, you expect something like a structure constant appearing on the right-hand side, but actually what is now new on the clones now on the right-hand side with spin -1 and spin +1. But what is new is now on the celestial sphere is that these clones also fuse into gravitons, so spin -2 and spin +2 conformal primary operators. And so we have computed this operator products, I mean, the set of operator products involving operators of clones and gravitons. We have taken the Einstein-Young-Mills amplitudes in 4 dimensions and then studied collinear limits. I mean, Tom yesterday in his lectures, he talked a lot about these collinear limits, and these collinear limits, they exactly give you the operator product expansion on the celestial sphere once you transform them into celestial coordinates and you perform properly the Mellin integrals. But completely complementary, this group of people have computed this operator product expansion by just sitting on the celestial sphere, let's say, and imposing first principles and consistency conditions. And then they got also this set of operator product expansion. So there's a nice consistency or striking consistency that you might say that, so 4-dimensional Einstein-Young-Mills amplitudes, they give powerful constraints on the celestial operator product expansion, or vice versa. If you take their results, then this celestial operator product expansions, they give powerful constraints on this Einstein-Young-Mills amplitudes in 4 dimensions. And as I will show you now in the sequel of my talk, that this operator product expansions are on also this Einstein-Young-Mills amplitudes, they're very important to understand and set up and construct the extended PMS symmetry. So let me now come to symmetries of celestial amplitudes. As already said at the beginning, in the 4-dimensional Minkowski space, amplitudes, we have not all symmetries present, and For example, we have now on the celestial sphere at null infinity, there are many more symmetries present, which will constrain the S matrix and which eventually give us non-trivial consistency on the amplitudes, in particular because now they are sensitive to both UV and IR physics. So one symmetry is, of course, Lorentz symmetry in 4 dimensions, which we have seen is now a global SL2C transformation. So it's global conformal transformation, which acts. So it acts if it acts on a particle number I. So then the amplitude has this transformation property. This is just for particle I. That's just comes from the transformation property of the conformal primary operators. And now you can also introduce another operator, which is given by this derivative with respect to the conformal dimensions h and h bar. So let's call it in this notation. And then you can see what it does on when it acts on particle number j. Actually, it shifts its dimension by +1. I mean, you can somehow see it because this is this operator, and that usually makes shifts on some functions. I mean, in that case, since it acts on h plus h bar, which determines delta, so it shifts delta by 1. And in fact, you can see that this corresponds to the spin components P0 plus P3. We will, so in fact, with the help of this function, we can construct the whole spin operator, but we will come in a moment to this. So, so this is related to the translation operator. And in other words, the translation operator is related to shifts in the conformal dimensions. And just a side remark, I've stressed that that these arguments of delta functions for the gravitational, for the gauge amplitudes, that they have different arguments, and that the deltas entering the argument of the delta function is different. And actually, you can show that you can represent now with this operator, you can, since this operator shifts the conformal dimension, you can essentially express the celestial gravitational amplitude as a gauge amplitude, just shifted by this delta, which in 4-dimensional Minkowski space means that it's just shifted by in space-time, by a space-time shift. So that's a quite nice relation we have also in our paper. Now, so this is one set of symmetries which is evident, but we will have more symmetries at hand once we understand or see how the soft theorems, or how what the soft theorems, what kind of word identities give us on the celestial sphere. So as usual, soft theorems play an important role in the consistency and in the structure of amplitudes. In fact, they constrain almost all amplitudes. So soft theorems mean that that the momentum or the energy of particle number S goes to 0. And then if you do this on an n+1 point amplitude, you get a series of soft terms, which are organized according to ordering parameter epsilon. So epsilon is smaller, so it's related to this PS goes to 0, and so you get this expansion in so-called soft split factors. This is a gravitational amplitude, and for the gauge amplitude you have this this series starting at epsilon squared. And it has been pointed out by Andy that soft theorems imply word identities for asymptotic symmetries, and this is what we want to investigate now in more detail on the celestial sphere. First, of course, we need to understand what these soft theorems mean on the celestial sphere, because now I mean, since we have integrated out over all energies, I mean, omega, I mean, what is now this limit? So how do we get such a soft expansion? So so we have performed Mellin transform with respect to all energies of particles. And now it turns out that when you send the omega, so this omega you integrate with respect to which you integrate, you get the typical IR poles in the Mellin transform. So this you can see as follows. So this is the Mellin transform of the S particle, which you want to which should go softer. And now you get such an expansion in the dimensions. So this is the expression in four-dimensional Minkowski space, and then you get an expression in terms of this poles. So you see that there are poles in delta goes to 1, delta goes to 0, and delta goes to -1, and so forth. And that they exactly correspond to the soft or split terms in the Minkowski space. And similar for the gluon amplitude. Let me just show you an example how this looks explicitly. So this is the n+1 gluon amplitude. So you compute the soft expansion, and then the leading piece here is given by this term. This is actually obvious if the particle S, which is the n+1 particle, has plus helicity, then that is exactly the split factor you expect after translating the four-dimensional split factor into celestial coordinates. But then this is the next leading term. Now, so we have the soft expansion, and we get for each of the soft limits, we get some symmetries. So more and more, so symmetries, so to say, become manifest. So we now investigate the soft expansion in the. So here we are at the principal series, which is delta is equal to 1 plus I lambda. But now we want to investigate our amplitudes when we move into this IR direction and look at these poles in the Mellin space. So we want to do this for graviton modes and see that the soft graviton modes can be related to BMS symmetries. In fact, recap, you might have heard yesterday that conformal soft modes of gauge bosons, they generate a Kac-Moody symmetry, and they correspond to large gauge transformations. And now we want to see what the soft modes of the graviton correspond to, and how they give rise to extended BMS symmetry. So we first, so we do have explicit field realization. We take a soft, so let's first take the soft graviton, delta goes to 0. So we take the graviton mode with delta goes to 0, and so this is spin -2. And then we can actually construct a stress tensor by performing a so-called shadow transformation, which is a well-known concept in conformal field theory. And then this shadow transformation shifts the conformal weight by 2, so it shifts from 0 to 2, and the spin becomes changes from -2 to +2. So here we indeed get a field, a conformal field of 2, 0, and by looking at this soft graviton mode, and you can indeed show that this is exactly behaves like a stress tensor. So it has the right Ward identity you expect for a stress tensor. It also has the right operator product expansion with itself and with T bar. And then from that, you can now construct an infinite set of Virasoro modes in the usual way, how you have learned it. Actually, from here, you see that the central charge is 0. Just a side remark, you might have wondered why we construct this stress tensor in this way by performing this shadow transformation. You could also, for example, perform a Sugawara construction of the energy momentum tensor. You take two clones delta goes to 0, and then you also take 1 with a shadow operation, and then this you can show that this also has exactly the properties of a stress tensor. This is just a side remark. Now we can also construct or we investigate a soft graviton mode, delta goes to 1, and then we can, for example, construct this field here, which is a spin +2 graviton, and we send delta is equal to 1, the dimension, and we take this derivative, and then actually turns out that this is a conformal field with these dimensions, and it has the following OPEs. I will come to later. I will come to a better definition of these fields, but for the moment, this is what we can take from here. That we have that this soft graviton mode delta goes to 1 gives rise or will give rise to supertranslation operator. Now, recall that I have introduced this operator which shifts a conformal dimension by +1. So this is.
If you could take one more question, that might be appreciated by a tool. Sorry.
Okay. So maybe if I get also the time.
I just wanted to ask if anyone has computed any loop corrections to the central charge.
Not to the central charge at present.
Cool.
But this is, of course, an interesting problem and question. So we had this operator which shifted the dimensions by +1, and actually we can now take this operator and construct. Since we have the stress tensor, we can construct a whole infinite series of modes by doing this counter integral. So we get a whole set of infinite set of modes which we can actually put into a generating function. And later in my talk, I will show you that this function actually corresponds to a fermionic soft mode. So this is gives a nice picture. I mean that we not only the bosonic soft modes but also the fermionic soft modes give a complete picture of BMS symmetries. So now we have let's just recap. We have now a infinite set of these modes P, which come from this translation operator, which in 4 dimensions. And we have, of course, this Virasoro modes from our stress tensor, and then we can compute this following algebra with now. I mean, for us, this C here is 0, and this is known as extended BMS algebra. So it encodes not only global conformal transformation but also local transformation, because they are all Virasoro modes L. And also super translation. So this is nice. So by looking at conformal soft theorems and Ward identities, we could derive this BMS algebra. And now actually we want to. So let me just summarize so far what we have. So we started on the celestial sphere. We had this global conformal transformations, which is given by the 3 generators, and then we had also translated the momentum operator, which gave, in particular, I mean, I stressed that this guy just shifts the dimensions, but then the other 4 components of the momentum operators you can easily construct, and this gives. So this is a global spacetime translation, which gives rise to a abelian subgroup of supertranslations. Now we have from the stress tensor we have obtained a full set of Virasoro modes, which then give rise to local conformal transformations, and we have constructed an infinite set of local spacetime translation which correspond to the supertranslation. So that means from here, which was a global BMS symmetry, now we have constructed a full local BMS symmetry on the celestial sphere. And now we want to take into account also fermions, because this gives a complete picture and also even extends this extended BMS algebra to the so-called extended super BMS algebra. And it gives a nice explanation, in particular, of our super translation operator. So we have started at the beginning with this conformal primary wave function. That was the simplest object. And of course, you can also introduce with spinors. We can also compute or derive conformal primary wave functions for fermions, and then for gluons and gauginos and gravitons and gravitinos. That's what we, that is very straightforward. And then you can again consider your Einstein-Young-Mills amplitude, now involving also fermions in 4 dimensions, and derive or write them in celestial coordinates and derive operator product expansion. And here's just a simple example. This is our operator product expansion of 2 gravitini. I mean, one of spin -3½ and the other one 3½ And then you get, as before, the operator product coefficients involve now this this beta functions. This is very common from when you look at operator product expansion on the celestial sphere. So this looks actually very stringy. And then here the fusion to graviton, I mean spin +2 and spin -2. This is just a sample of some of our operator product expansion we have obtained. So now again we can look at fermionic soft theorems. Now again, you get residua in the Mellin amplitude, and now we have residua at delta goes to 1/2 and delta goes to -1/2. So if this is an amplitude which involves, for example, gravitini, and indeed you can now just look what such an amplitude behaves. This is now just in lines as I showed you for the gluon amplitude before. So this is an n+1 point amplitude involving a gravitino, and then n states with any spin L. So we are in particular interested in this gravitino. It's the first place here, and now the soft expansion here now, so this delta goes to 1 singularity. Now you encounter on the celestial sphere. Now it assumes the following form. So indeed the leading piece, the leading singularity comes from this delta goes to 1/2. So this gives the soft mode corresponding to delta goes 1/2, and then there are some, as usual, some celestial coordinates and so on. And what we actually will do now, we will perform some complex integrations here on the right-hand side, on the left-hand side, and we will get some nice Ward identity. And indeed, you can derive many of these soft limits, and there's because now we have supersymmetry. So actually, I forgot to stress that we construct our bosonic and fermionic modes in 4 dimensions, and then with them we construct the conformal primary wave function. So we have supersymmetry in the 4-dimensional target space, but we only take the supersymmetry, or only make advantage of the supersymmetry in the 4-dimensional space by grouping this conformal primary wave functions into SUSY multiplets, and in particular by taking the supersymmetric Einstein-Young-Mills amplitudes with involving gravitino. But so there's yet to be seen whether there's also supersymmetry on the celestial sphere. So this is when I talk about supersymmetry, it's important that this supersymmetry in the 4-dimensional Minkowski space. And but nevertheless, I mean, there's this supersymmetry in 4-dimensional Minkowski space. That gives an intriguing relation between all the soft modes. This is simply a fact of supersymmetry in 4 dimensions, that that the various soft limits are simply related. I mean, this soft limit we have encountered for the bosonic case, delta goes to 0 and delta goes to 1, and now to delta goes to 1/2. Now, recall that we have from the soft graviton mode, delta goes to 0, we have constructed a stress tensor by performing the shadow transformation. Now you can imagine that we could do something similar for this gravitino mode. So now we take the soft mode, delta goes to 1/2, and takes this gravitino and take a shadow transformation as it is dictated, given by this shadow formula I showed you before. And then we get something which correspondingly to the stress tensor, we should now call a supercurrent S. And indeed, when you do this manipulations here, that's what I said before, this complex integrals, I mean, then there's some complex integrals on this. You can derive a Ward identity for this supercurrent, and you can extract some operator product expansion for this supercurrent. In fact, it does almost what you I expect from what you expect from a worldsheet supercurrent. So it shifts the spin from J minus 1/2 to spin J, so it shifts by 1/2, but it also shifts this dimension, and this is the antiholomorphic supercurrent. But so we have here constructed a supercurrent which from this delta, from this fermionic soft mode. I mean, and then now we can, as before, as we did for the stress tensor, we can now construct from this supercurrent a whole infinite set of modes in the usual way, and then of course ask what these generators are doing, or what algebras I fulfill. Let me also tell you that then this modes G, they are related to the SUSY generators in 4 dimensions. So you can write a relation between this modes G 1/2, this lowest mode, and the 4-dimensional supersymmetry, I mean the Q and Q bar. And now, as promised, I can now express this. Note that this is, we have, when we still talked about the bosonic case, we have constructed this generating function for the super translation modes. So this was the super translation operator. And then I promised you that I will give you a nice formula in terms of soft modes. And in fact, what we can see is that if you take a product of the supercurrents, holomorphic and anti-holomorphic, that is exactly what this P is. So there's now, this picture closes nicely now that we have looked at the soft mode, delta goes to 0, soft graviton mode, delta goes to 0 and delta goes to 1, which give us a Virasoro and super translation modes. And then we have looked at the fermionic soft mode, delta goes to 1/2, which give us at first this supercurrent, but secondly, it also gives this, through this bilinears, it gives a nice expression for the super translation operator. And now you can compute the algebra. So we have already computed the algebra involving just the P's and the L's, but now we want to see what the full algebra is also involving these modes of the supercurrent. So that is what we find, what is in the box here. So this is easy to understand, the first line. I mean, I told you that these G's are related to the 4-dimensional SUSY generators, Q and Q bar. And then when you look at the 4-dimensional SUSY algebra, then it closes on the momentum operator, P. And then on the celestial sphere, this momentum operator is related to the super translation operator. So it's kind of clear that this anticommutator closes on the super translation operator, which on the other hand tells you that it is not a super conformal algebra on the worldsheet, because there you would just expect that the holomorphic and anti-holomorphic fields decouple. So it's quite different algebra on the celestial worldsheet. That's why I stressed that we use only supersymmetry in the 4 dimension to specify and bookkeep our multiplets and also take our supersymmetric Einstein-Young-Mills amplitudes, and then we went onto the celestial sphere and extracted operator product expansion and extracted this supercurrent, and this then found this algebra, which is now the supersymmetric generalization of our extended BMS symmetry I showed you before, and this comes from studying SUSY in 4 dimensions. So it's an n-1 supersymmetric extension of the previously shown extended BMS algebra. So it involves the superrotation, which are the modes of the stress tensor, the supertranslation, and then the supersymmetry from the 4-dimensional supersymmetry encoded in this G's or in this supercurrent S. So let me now summarize my talk. Of course, there are many open questions, and that's actually what is my summary, that I want to give some further directions which need to be understood. So, of course, now we have talked a lot about the relations between soft theorems and symmetries. And now the question is how understand the symmetries at the quantum level. This is, of course, immediately also related to what extent the soft theorems are renormalized. And then there was already the question, what is the Virasoro central charge? So it, of course, it might appear at one loop through some regulator, for example. And then there seems to be a beautiful link between the high energy or large lambda limit, where the string worldsheet becomes a celestial sphere. So this might give us a link of understanding, at least in this corner, the celestial conformal field theory better. Or see how it is related to a free worldsheet CFT. Of course, we want also to understand better the nature of this celestial conformal field theory, which then ultimately is the object to be used for computing amplitudes. And that would also give us then a holographic description of flat spacetime. But for that, we need, for example, to understand conformal blocks. And then eventually, after uplifting it to an ADS3 CF2 holography, I mean, we can then see how this flat space-time holography works. So there are many open questions, and so that thank you for your attention.
Thank you very much, Sabrina, and thank you for organizing this great workshop. So yeah, my talk will be about conformal primary wave functions and celestial Goldstone modes. So this talk is based on the following works. This one was done in collaboration with Andrea and Andy, and these two are work with Andrea and Sabrina. So this one is supposed to appear very soon. So if you have any questions or comments, don't hesitate to interrupt. So the aim of my talk is to present a unified treatment of what I call celestial Goldstone modes. So the Goldstone modes are arise when you take certain limit, which are called conformally self-limits, of conformal primary wave functions. And I also want to discuss how these Golson modes are related to asymptotic symmetries and their associated net charges at null infinity. So the focus of my presentation will be about conformal primary wave functions. Stephan already introduced most of the ingredients, but I will review that from scratch. And as we will see, these conformal primary wave functions are large gauge equivalents of these Malin transform plane waves that he talked about. So large gauge is means that these are gauge equivalent, but these gauge parameters do not die at scry, and of course are very important in all this discussion in asymptotic symmetries. So I will first review what are these conformally primary wave functions and what are their important features. I will then turn to certain limits of these functions, which, as we will see, generate Goldstone currents on the celestial sphere. And finally, I will make some comments about how this story carries over very nicely for a very rich extension, which has to do with subleading and subleading theorems. Okay. So the definition of a conformal primary wave function, so I will just focus on the massless case and mostly on spin 1 and spin 2 cases. So the defining property is that they are a solution of 4-dimensional Maxwell's equation that transform as a conformal primary of certain weight h and h bar under an SL2C transformations. So what is good is that Stephan already, I mean, we almost have all the same notation, so it's pretty convenient. So x here are the Cartesian coordinates in Minkowski, and I will describe a reference point on the sphere, on the celestial sphere, as WW bar, plus or minus denote incoming and outgoing wave functions. And so this spin 1 gauge potential transform as a Lorentz vector under SL2C. And let me use that. And as a primary, when you do a Möbius transformation on the sphere angles with weight h and h bar, which are respectively the sum and differences of the conformal dimension and the spin. So an explicit expression that satisfies this property was found and takes the following form. So it involves this vector q mu. So q mu is a null vector that is pointing towards a point on the celestial sphere, WW bar. You can use this explicit parameterization for this vector field. And when you take the derivative with respect to W of this vector field, you basically obtain the polarization vector for plus helicity. And when you take this index A to be W bar, you land on negative helicity. There is also a plus or minus I epsilon prescription that is encoded here, depending on whether it's outgoing or ingoing. So this is the object we'll be working with. And you can rewrite, it's actually convenient to rewrite this, this object and split it in two pieces. This piece here is a residual gauge transformation parameterized by this parameter alpha. And the reason why I'm splitting this guy into two pieces is because this V mu here is nothing but this now famous in this workshop Mellin transform of the plane wave. So as Stephan explained, basically if you have a massless particle with a form moment of p mu, doing this Mellin transform will exchange the energy for this conformal dimension delta. And then you have a helicity factor here. So as you see, these primary wave functions are essentially this Mellin transform plus a residual symmetry. Notice that they are intrinsically satisfying some specific gauge conditions. They are Lorentz and a radial gauge. And now you have all these shadow primaries. So the conformal shadow transform of celestial primaries are equally good conformal primary wave functions. What I mean by that is that they also define solution of Maxwell's equation and transform also as a primary. So you can compute what is the shadow transform of this object. This was done in this paper. So here it was done using the the embedding space, the uplifted primary and then projecting back. But basically, what you get is this very simple expression. So x squared is, so x is the Cartesian coordinates. So I will denote the shadow transform of this object by this tilde here. So the important thing to notice is that the shadow transform transforms you a primary of a dimension delta to a new conformal primary wave function, but now of dimension 2 minus delta that I will call delta tilde. It also flips the spin. So everything I said basically is valid for a spin 2 primary wave function. Of course, now we are looking for solutions of linearized Einstein equations, and the explicit form for these primaries is given by this. So you can see actually that is looking very much like the square of the spin 1 primary. You can also split into pieces. The first one involved is just the Mellin transform of plane waves time a polarization tensor, and up to now a residual diffeomorphisms parameterized by this zeta function, this zeta vector field here. Again, you have equally good primaries, which are the shadow transform of this expression, which have now dimension 2 minus delta. So notice that, again, these primaries are in a specific gauge, fixing. They are in the Donnay gauge, and that's why the Einstein's equation reduced to box of H equals 0. We can introduce very natural inner products for spin 1 and spin 2 respectively, and evaluated on a certain Cauchy surface. This H is the trace of this guy. So the inner product of this Mellin representative, which are this V, I recall, are just Mellin transform the plane wave, was computed by Sabrina and Xu Hang, and they found that, so if you Mellin transform the plane wave inner product, you find that the Mellin representative form a complete basis, a delta function normalizable basis, when their dimension lies on the so-called principal continuous series. So when delta take the form 1 plus I lambda, lambda being real. So this inner product is pairing you modes of dimension 1 plus I lambda with modes of 1 minus I lambda. So now you know that you have a basis, you know that you can go back and forth between the Mellin space and the usual momentum basis. But now, as we have seen yesterday, and also Stephan talked about it, they are very interesting modes which have dimension delta that doesn't lie on the principal series. For instance, delta equals 0 is an interesting case, or delta equal to 2. So we wanted to understand how these modes, which do not lie on the principal series, are related to this basis. And so in this paper, we found that there is a way that you can actually express a primary wave function with an arbitrary conformal dimension delta in terms of a certain contour integrals of the primaries that lie on the principal series. So this contour integral involves this delta hat distribution here. So this is a generalized distribution in the complex plane. And so basically, if you take this delta here to be on the principal series, then this delta hat reduces to the usual Dirac delta function, and this identity is just trivial. But when you have dimensions, primary with dimension, depending whether they lie on the right or on the left to the principal series, then these generalized delta functions can be seen to be the Mellin transform of this exponential here, and equal to and gives you some gamma functions. And so when you plug this into this contour integral here, the residue theorem will pick up the poles of the gamma function. And this is basically how it works. Nu is a regulator that you take to 0 at the end. So what I want to say here is that there is, you can obtain the arbitrary conformal primary with any dimension you want by doing these contour integrals of the principal series, guys. So now that we have that, we can now compute the inner product of celestial primary wave function with any delta. And this is the expression that we find. So again, this delta hat here, when delta and delta prime, when you take the inner product of two different primaries, when they lie on the principal series, you recover basically the usual pairing with the lambda and lambda prime modes. But in general, this is the expression you get, and this should be understood as valid under certain contour integrals. So good. So now that we have that, we have understood this. We can take any operator and make a mode expansions in terms of the modes on the principal series as such. So here these n are just some normalization factors, and these a and a dagger are creation and annihilation operators in the conformal basis, which satisfy these commutation relations. So we can use that expansion to define a quantum mode Q, which carries a dimension delta and index A, which is essentially evaluating the inner product of any mode expanding as such with the primaries evaluated on a certain Cauchy surface. So you can check that by doing such a definition, this quantum operator shift the gauge field in a inhomogeneous way as such. So this is the commutator of involving this quantum mode, and it induces a shift in the field. So of course here this is focused on spin 1, but mutatis mutandis, you can get everything similarly for the spin 2 primary. So that was basically everything we need to know about these primary wave functions. And now I will discuss how these Golson currents appear when you take certain very interesting limits in their conformal dimension on the sphere. So the question I want to ask is, what can we learn from these conformal primary wave functions? What can they tell us about this very rich asymptotic symmetry that Geoffrey talked about yesterday? And more broadly speaking, can we also get some sort of insight into the celestial version of the infrared triangle, so which is this relationship, beautiful set of relationship between asymptotic symmetries, subtheorems, and memories. So if you want to do that, a good thing to do is to look at what we call the conformally soft limit. So as Stephan explained, we are in the usual momentum basis. We look at energetically soft modes. But now by doing this Malin transform, we trade this energy for the dimension delta, or equivalently for the weights h and h bar. And this is what we call, taking these limits on the weights is what we call a conformally soft mode. It's actually, the conformally soft objects go actually beyond this case where you have a holomorphic structure. It's actually, I mean, We will see that later. So there is an extended, if you want, definition of what is a conformally soft limit, but we will just start with looking at this case. So let's see. So if you take this conformally soft limit where the dimension goes to 1, you can directly see from the expression that I presented in the beginning that the spin 1 primary, because this thing is 0, becomes a pure gauge transformation parameterized by this alpha evaluated when delta is 1. And the shadow transform is actually reducing to the non-shadow mode because you take delta goes to 1. So both of them degenerate to the pure gauge mode. So if you can take this this guy and write it in boundary coordinate and expanding near scribe plus, and then what you see is that this mode basically is given by this derivative here of a parameter epsilon, which is equal 1 over z minus w, which is the large gauge parameter. So in other words, these Goldstone modes, I mean, this primary, when delta goes to 1, is nothing but the Goldstone mode associated to broken large U1 gauge symmetry at null infinity. So a similar story happens for a past null infinity. And of course, we know that there is this antipodal match and so on, but I will just focus on scribe plus. So you can compute the inner product now with this Cauchy surface pushed on scribe plus, and you land very nicely on the soft photon charge associated with U1 symmetry for this specific epsilon. So very importantly, you can construct an object that transforms as a 1, 0 out of this mode, and this current is called Jz, is a Kac-Moody current on the celestial sphere, and it satisfies this OPE with any operator of dimension delta on the celestial sphere. So this OPE relationship is really the celestial representation of the leading subphoton theorem. So now there was an important subtlety that needed to be addressed is I told you that we had this pairing between modes of weight 1 minus I lambda and 1 plus I lambda. But when lambda goes to 0, when delta goes to 1, there seems to be a mode that is missing because the Goldstone mode seems to be alone and seems to have missing a symplectic partner. So what is the symplectic partner? So if you look very carefully at the solution, you can actually find as a hidden logarithmic branch a new 1, 0 primary. This is what we did in this paper, and we call this the conformally soft photon. This is the explicit expression for it. You can check that it's transformed as a 1, 0, so h is 1, h bar is 0. And it's not a pure gauge mode. And importantly, it's really the guy that is paired with the Goldstone modes. So now let's turn to gravity. So Geoffrey and Andy yesterday presented in very great details what it means to be an asymptotic flat spacetime. So this is the expansion of the metric which defines such a spacetime when you approach this future null infinity here. It involves the boundary mass aspect, the angular momentum aspect, and this function here, which is not constrained by equation of motion, which is called the gravitational data, or sometimes the shear tensor. The time derivative of this object is the News tensor and describes the presence of gravitational radiation. So I think we all use the same coordinates and notation, so that's great. So as Geoffrey explained, we know that we have this asymptotic set of spacetime is preserved by acting with a super translation vector field which takes this form and is involving this arbitrary function f of the angles. If you look at how this vector field acts on the angular part of the metric, which expands as such, so gamma AB is the unit round sphere, and then you have this shear here that appear with the power of r, then you can see that this is how the super translation acts. So there is a part that is proportional to their derivative of CAB, plus importantly, an inhomogeneous part, which is also called times the shift. So this is really are related deeply to what Andy explained, namely the fact that you have degeneracy of vacuum, and this super translation is relating the different vacua. And in turn, this leads to the displacement memory effect. So what does it have to do with this primary wave function? Well, again, now if you take the conformally soft limit, delta goes to 1 of spin to conformal primary wave function, you land on the pure diffeomorphisms parameterized by this zeta here. And as Cry, you can realize that indeed this vector field generates the following shifts on the shear with this parameter f, which is this super specific form of super translation. So again, this primary wave function, when theta goes to 1, is really the Goldstone mode associated with super translation symmetry breaking at Scry. Again, there is a subtle conformally soft graviton to which is paired to the Goldstone mode. It's very similar to the spin 1 case. Now, what is funny about this this mode is, as Stephan mentioned, it leads to an object which has weird weights on the celestial sphere. So this delta goes to 1 mode has actually transformed with weights 3½ minus 1/2. And its inner product with the quantum mode again lends you the soft part of the super translation. Now, very interestingly, if you take the descendant associated with delta equals to 1, so you take 1 derivative of this guy, you can construct an object that is called a super translation current PZ, which now, because you take the descendant, has weight 3½ plus 1/2. So the OPE on the celestial sphere that is satisfied by this object has these funny properties that, even though, I mean, it's not a holomorphic current, but it has this, shares some holomorphic properties, and importantly, it shifts, I mean, Stephan explained very well, it shifts the weight of 1/2 plus 1/2. I mean, the way he put it is that it shifts the conformal dimension, which is the sum of these two, by 1 unit. And you can see this shift by comparing how it appears from the momentum basis, because in the momentum basing, you have the energy here on omega. So when you Mellin transform this relationship, you see that basically, because you have this power of omega, delta will be shifted by 1. So now let's turn to also a pretty nice story, which has to do with so-called super rotation symmetry. So I will clarify what I mean by super rotations, because there are several names and nomenclature, I mean, about that. So let's look at the celestial graviton, and there are actually now two other modes, apart from the delta equal 1 I just discussed, that reduce to a pure diffeomorphism. The first one is the primary of weight delta equals to 0, which takes the following form. And the second graviton modes is the shadow transform of this one. So these guys are related by a shadow transform. So it's the shadow primary of weight now of dimension 2. It's also a pure diff. Now, because this guy satisfies the Donnay gauge, this psi has to satisfy box psi equals 0. So if you want to identify this thing with some Goldstone mode associated to some superrotation, you first want to be careful that you are working out with the superrotation not in boundary gauge but in harmonic gauge. So here I want to emphasize that I'm working with superrotation that are parametrized a priori with an arbitrary function of the angle. I will comment on that later. So superrotation harmonic gauge takes the following form. So this, the blue are the difference with the usual boundary gauge. And they have the following action on the sphere component of the metric. So the action on the unisphere metric is, this is basically the conformal killing equation. So if you have a conformal killing vector, it will not change your unisphere. And this is the usual, the original, if you want, boundary condition that were imposed in the 60s by Bondi, Messner, and Sachs. If you look for globally well-defined killing vector fields, then you just are not allowed to change this round sphere metric, and you land on with the 6 usual Lorentz transformations. Now, Glenn, Barnish, and Cedric Troussard thought maybe it's a good idea to relax this and to allow for vector fields that are only locally well-defined on the sphere. And in this case, you will violate this at isolated point. So these are the so-called superrotation of Virasoro kind of superrotations. And then Campilli and Lala later, I will comment on that later, thought that maybe actually it's interesting for a reason I will explain later to allow for vector field that will change this round sphere metric. And in this case, this YA is any function of Z and Z bar. So this has led to different proposals for what is a superrotation, and I will comment on that later. Again, the superrotation shift the shear as follows. So I said before, there are 2 primaries that can be associated with superrotations. The shadow primary of weight 2 gives this shear, has this shear at null infinity with this expression for the vector field. So if you take the Lie derivative associated with this vector field, you will see that it's naturally associated to a kind of Virasoro kind of superrotation because it violates the conformal Killing equation at isolated points. Now the primary with delta equals 0 has this shear with these vector fields, and acting with this vector field will just change which is gamma AB, so it will modify the round sphere metric at leading order. So this is what the reason why I will say that this primary is associated to differs 2 kind of superrotations. So now if you want to compute the charges associated with this symmetry, you have to be careful. So this is usually how you do. You take the so-called higher-wire symplectic structure. And so Geoffrey explained that yesterday. So it's basically the integral over square of a presymplectic form that involves 2 variations with respect to a background. And I want to take one of the variation to be one of my primary wave function, which are pure diffeomorphisms. But now, because the boundary falloffs are violated, some are violated just locally and some are just violated, you need to renormalize your symplectic structure. And the renormalization was worked out in this paper by Geoffrey, Adrien, Romain. And so basically, the reason why you can do this renormalization is due to the fact that so this presymplectic form is the anti-symmetrized variation of this presymplectic potential, and there is always this freedom, or sometimes called ambiguity, to shift this presymplectic potential. So when you do all that, so the reason why you really need to renormalize is because if you compute this presymplectic form, you will find that it blows up like R at scry. So by doing this renormalization, you basically get rid of this piece and you get something that is finite. And what we did, I mean, it's very similar to this paper, but we're working in different gauge. But at the end, the result is that. So this coincides with the superrotation charges, but now with YZ being any function of Z and Z bar. And this expression has also been worked out in this paper. So this charge associated to this shadow primary gives you immediately this relation, because YZ is 1 over Z minus W. And this is nothing but the 2D stress tensor that was constructed by these people from a reverse engineer of the subleadings of Graviton theorem. Now you see that this stress tensor can be readily obtained from this conformal primary wave function. So it's of course a 2,0, and it was shown that its insertion in a S matrix was giving a Virasoro-Ward identity. So now we have this other mode, this non-shadow mode. And as you expect, the shadow mode gives you basically the shadow transform of the stress tensor. So this is the 2D shadow transform of a 2,0 primary. And it gives you an object which has opposite helicity and weight -1,1. So this is what we call the shadow stress tensor. So the summary is that you have these two spin-2 modes, these two Goldstone modes associated with superrotations. They are shadow transform of each other, and they lead respectively to the stress tensor and to the shadow stress tensor. And after renormalization and this renormalization procedure, commute with the shadow. So now I think this story somehow shed some light on some discussion about what is the proposal for superrotations and the relation with sub-theorems. So originally we had this kind of Virasoro-Ward identity. So the charge was found by Glenn and Cedric, and the Ward identity was studied by all these people. And Freddy Cacceso and Andy Strominger found that knowing that there was this symmetry, it inspired them to look for a new sub-Graviton theorem, the so-called Subleadings of Graviton theorem. And this theorem was shown to imply the Ward identity for the Virasoro symmetry. But this relation was not quite going the other way around. This led Campilli and Lada to propose that we should enlarge the phase space to accommodate for arbitrary function of Z and Z bar. And if you do that, you can show that there is a one-to-one correspondence between sub-theorem and the Ward identity. Now, what our analysis is pointing at is that for the specific mode we looked at, they are related by a shadow transformation. And so if you allow your asymptotic symmetry group to be closed under the shadow transform, you can make all your way down from the Virasoro-Ward identity to the soft-Graviton theorem. So that was about these Goldstone modes. Now, in the last part of the talk, yes, there's some questions.
Yeah. Do you expect related stories for like delta equals 3 and 4 and so on, despite that
Yeah.
they're not big?
I will. This is exactly what I'm going to talk about.
Oh, sorry. Okay.
Thanks. No worries.
And then a question from Atul, I think.
Does the shadow of the stress tensor also satisfy some conservation relation?
I mean, it satisfies a kind of you know, OPE with which is non-holomorphic, of course. It's a funny thing, yeah.
I mean, the T would satisfy d bar T equals 0, like a conservation relation, classically. Yeah, and is there some, on doing a shadow transform, does that become some PD for T tilde?
I mean, yeah, I mean, then you, it's more tricky what it is because this is not a holomorphic current, so it's not so clear what it becomes. But there is a funny relation that you can obtain, but it's not the usual.
So it doesn't have a geometric interpretation of any kind.
Let's just.
I mean, not. Yeah, sorry.
No, like there might be something in the next talk that might hint at something like that, but I agree, like it's something.
I'll ask later.
It's a funny object, yeah. Okay, so as Adam just asked, what happens if you look at other dimensions? So just to recap, this is what we have so far. We have spin 1 with delta equal 1. This is the Golson mode of large U1 symmetry. The wire identity is the sub-photon theorem, and you have a U1 catch-Moody current. For spin 2, you have super translation and super rotations. And you have a leading and subleadings of Graviton theorem. And again, you can construct a very nice current. This is 2,0. This is a 3/2 minus 1/2, plus 1/2, sorry.
Shamik had a question too. Sorry, I just noticed.
So I just wanted to ask, so this D phase 2, so does this also have singular transformations or just the smooth ones?
Yeah, I mean, when I mean, okay, you can just, some people just restrict to smooth D phase 2, but when I say D phase 2, I have in mind that in principle, you can also have singular.
Also have the singular ones. Okay, thanks.
Yeah. So, good. Thank you for the question. So, yeah, so this is the thing I already talked about. So now we know we have a subleadings of photon theorem and even a subleadings of graviton theorem. But then the relation with this wire identity with asymptotic symmetry is quite tricky. I mean, I will come to that now. So indeed, we have the existence of the subleadings of theorems. So this is the leading subfactor that goes like 1 over the soft energy omega, and then you have this subleading part, which goes like omega to the 0. And you have a subleadings of graviton theorem. So this is the leading factor, the subleading, and here is the subleading. This is the explicit expression for what are the subfactors. I mean, I think Thomas talked about that already yesterday. So the existence of these theorems seem to imply wire identity for corresponding asymptotic symmetries, but there is no remaining conformal primary Goldstone mode. So if you look at all these primary wave functions, you look for extra pure gauge or pure diffeomorphism, you will not find anything because there are no. So this raises the question, to which extent can we still interpret this Q delta as a soft charge for these wide identities? So let me mention some works that went into this direction. So Campilli and Lada have discussed how you can actually get the subleadings of photon charge from an over leading gauge parameter. So they looked at some gauge parameter lambda that satisfy inharmonic gauge, and they looked at something that behaves like with this overleading piece when you expand around scry, and they show that there is a way you can actually get the subleadings of charge. So the subleadings of charge was found by a reverse engineer from the wire identity, and it involves now a vector. And Campilli and Yala show that if you make this if you relate this overleading arbitrary function mu to this vector field, you can actually get or construct the subleadings of charge somehow. So there is another work that has constructed a celestial current associated with with a subleading subphoton theorem, and this was done by Mina and Andy 2 years ago. So they looked at, it was a different approach, and they looked at now a subleading components of the gauge potential. So this one here means that is the 1 over R piece of the expansion of the gauge potential. And what they show is that you can actually express the soft charge as difference of the value essentially of this quantity at scry ++ minus the one at scry ±. So thereby showing that there was a non-zero effect associated to this subleading component. And they have also constructed a celestial current on the celestial sphere that satisfied the following identity here. So again, you can recognize now that we are kind of used to a funny feature of this object, because you see that it decreases the weights h and h bar by a half. So again, this can be seen as the celestial realization of the subleadings of photon theorem. But now the residual gauge fixing that were used is not actually compatible with our primary wave function. So for instance, there is some gauge condition that is just not compatible with the gauge in which this primary are. So these require a different analysis. But there is this hope that, of course, at the end, you should, since it's all this has to be associated to some physical effect, it should not depend on all that. So you should be able to construct a current also from these subleading primaries. So, and as Adam guessed, I mean, this obviously will come from looking at these dimensions for spin 1 and this one from spin 2. So the goal is that, so this is what we're working on, is to extract the subleading wire identities from these primaries in spin 1 and the subleading wire identity from the spin 2 guys. So again, I want to say that, of course, the relevance of this conformal dimension has been studied in this paper. For instance, Alfredo from recursion relation and Tim Adamo and collaborators from ambitwistor strings, and also in these papers and probably others. So as usual, when you work out the details, there are many subtleties that are involved. For instance, you have an infinite towers of logarithm that appear in the expansion. You also have to be very careful of how you treat all these contact terms. You might also need to prescribe some good fall-off behavior in U for the fields. And again, as usual, the prescription of boundary terms in the charges are of great importance. So this is work to appear. So I'm just concluding here by saying that I think now we are coming with a good understanding of what is the analog of the IR triangle in this conformal basis. So the corner of asymptotic symmetry is played by the celestial Goldstone mode. they are actually naturally paired with the celestial memories. I didn't talk so much about that, but maybe another day. And also we know that very remarkably, we also have conformally theorems that arise now as certain limits of the dimension delta. So people, I mean, it was already mentioned, and maybe we will hear more in the rest of the workshop. So I will stop here. So it's great to see all you guys working on this area. So I want to thank you very much for listening.
Lovely graphic. Thank you, Laura. Let's handle a couple of questions now if there are just for Laura. I noticed the ones in the chat seemed actually pretty appropriate to like ask both Stephan and Laura if Stephan is still around. Oh yes, okay, so let's start with Prahar, I guess.
Hi. So I didn't fully understand, what is this gauge problem that you were mentioning with regard to the subleading?
Oh yeah, I mean, it's not really a problem. It's just this thing that if you look at what has been done, for instance, by Mina and Andy, they use a residual gauge fixing. For instance, you impose that AU is 0 on scry, something like that, and this is not true for a conformal primary wave function we are working with. So our goal is really to recover this thing from this primary wave function and construct a current from that. It's just some incompatibility in the residual gauge fixing that at the end should not matter at the very end, but at the intermediate stage are important to look to.
Yeah. So I think I did understand this correctly then. So you can actually bypass all of these things if you try and work directly with the field strength without needing to work with the gauge field or impose any gauge condition whatsoever. So in a series of papers that I wrote last year with Tempo, we showed all the subleading, of course, the leading soft theorem as is usual, and the subleading soft theorems using only the field strength without ever having to impose any gauge. And also something, we generalized it to all dimensions, odd as well as even dimensions. So in particular, this boundary condition that Andy imposed, which is AZ1 equal to 0, is just the same thing as imposing FRZ is matched. So you impose a matching condition on FRZ, which is a gauge invariant quantity.
Okay.
I mean, I think it's a good thing to, like, we were interested in these operators that are like the scattering states, not just the field strengths. And there's a bit of subtlety there. So.
Yeah, but for the soft theorems and for the Ward identities, being that they're gauge invariant statements.
Sure. Yeah.
Sure. No, sure. But in the end, I mean, like, you can gauge away like a lot of these large gauge transformations too. And like, I think part of the point of some of this stuff is to be careful that like you're taking for granted the symmetries that you're proving the Ward identities for in a lot of like these manipulations going from Mellon basis to CPW. So it's
I haven't done anything in this whole Mellon basis, so I'm not aware of the complications that arise generally. But just from the the old language that we used to use with matching conditions and whatnot, you don't need to talk about residual gauge transformations. You can just work with the field strength, and you just always pick up, you get all the right asymptotic symmetries without ever having to impose local gauge conditions.
Yeah.
So I was only thinking if something similar could be done in this conformal wave function story.
I think that still doesn't take care of the issue with contact terms. So we still need to expand the field strength, and that gives rise to contact terms. Yeah,
I'm sure there are issues.
There are a lot of subtleties involved.
By the way, in the works that we also discussed all the log terms. So that's definitely one thing we resolved there, but we didn't get
the log terms are in the contact terms for some of us. Those are things. So
they are just really in the contact terms actually.
I think
but we dealt with the log terms. I don't know what contact terms you're referring to, but we did manage to figure out the log terms.
So the issue is that you can have logs, and this was one of the questions in the chat. You can have logs that come from the fact that you have now sources, right? So like obviously like the equations of motion. You actually also get logs just in the pairing of two free gravitons, and you have to be careful with how you interpret that as a soft theorem, because you can get a log U appearing and then integral D of log U isn't a soft theorem.
Yeah, we had those, and we figured out a way to handle those.
Because okay, we'll look into that stuff, but it's a little bit of a different. It's not the same.
I'm sure there's a difference because we're not using exactly.
Yeah. I'm not saying that the logs. I mean they have appeared in many settings, but yeah, I have something specific in mind, which of course not clear to understand because I didn't present the expressions. But yeah.
All right.
Great. I think the next question was Ali.
Yeah, thank you.
Yes, I just wanted to see, to ask what is the physics of these conformally soft modes? I mean, in what kind of process can you generate this mode? Maybe it's a naive question, but
memory effects.
No, I mean, yeah, it's just the analog of everything you know about the IR triangle, but in a conformal basis. So in particular, you have the encode memory effects. The same one you know. I mean, plus maybe new ones.
Yeah, but you said that this conformally soft mode is not a pure gauge, right? So it's like really a physical field configuration.
Memory effects aren't pure gauge.
Yeah.
Yes.
I mean, even the pure gauge are physical in a sense. So
yes.
They're all physical. Now, the memory effect associated to the modes that are not pure gauge or pure diff are somehow less familiar, maybe with.
I thought maybe it has something to do with tail effects in the discussion of gravitational waves and so on, but maybe we can discuss about that later.
Yeah, I mean,
what do you want to call it? Tail? This is
tail.
There's oddly.
Sorry, you asked a question?
Oh no! I'm saying like it's not like the tail that you might have in like an odd dimensional like a celestial sphere. This is just like the statement that you have like parts of the like the metric will give you like a step function, for instance. That's not a tail, that's a memory.
Okay.
But I think we can we can discuss in the.
Yes. I will ask
because
later.
Yeah, and I think the nicest example of the conformally soft modes being written out is Laura's paper with Andrea and Andy, the first one of them.
Yeah. Yes.
Thank you.
Anna?
Yeah, thank you for the talk, Laura. So
thank you.
I have a basic question about the statement at the beginning. You showed that any delta equal, arbitrary delta modes can be expanded on the principal series. And I was just wondering whether you guys have thought about an inverse of the statement in the sense that, if you have a mode on the principal series, can you expand it in terms of, say, some like arbitrary delta modes, perhaps some calculations on delta 1?
Yeah, I mean, yeah, that's a good thing. I mean, we didn't write an explicit expression, but we could, I guess we could.
I think we might have it in like an old drafts footnote, something. I mean,
okay.
like I've summed over things before. I remember, but like we can find it at some point.
So is it the case? I'm just wondering, would it be the case that, like a principal series solution can be expressed as some like infinite sum of
I think so, probably. Yeah.
Integer.
Yeah. It's just very, I guess, cumbersome, but.
Okay, but
yeah, I mean, like, because especially once we had these gamma function definitions of things, right? Essentially, like, I think there is a sense in which, okay, so if you take the paper, like if you take our paper together, Laura, you look at the way that we've written the delta function in terms of a gamma function. When you actually evaluate the check, you're essentially summing over the poles there. So I think that effectively that might be doing it, depending on what argument you say you're trying to localize it to. I think that at one point we wrote something like that. I have to double check that it's actually in the right direction.
Okay, thanks.
Shruti?
Hi, thanks for your talk, Laura, it was great. So I also had a question to what Anna asked. So you talked about writing the modes as integrals over the principal series. Did you think about it at all for massive fields? And like, do you know if it works out too, because you have the Green's function and stuff?
Right. I mean, it's not something I looked at. Of course, we just look at masses case. So let's see. I mean, for the massive case, yeah. I mean, you have this bulk to boundary relation that replaces the Mellin transform. So this should be, yeah. Yeah, I mean, that's something we didn't work out, but I mean, this should be some way to do it. I mean, yeah.
Okay, I wasn't sure whether what you had done with like the contour integrals and stuff was specific to Mellin transforms for some reason, or
right in our because I mean this generalized delta function was inspired by the inverse Mellin, so there should be some it should be modified for the massive case. That's all I can tell you because we haven't looked at that yet.
Yeah. Okay. Yeah. Great. Thanks.
I mean, sometimes, so the thing that you'd have to generalize if you wanted to write it out would be that for the Mellin guys, you're taking like the Mellin inverse Mellin transforms identity to define the distribution. So you'd want to look at whatever completeness relations are there for the scalar. So like those mu or nu, like there's this measure factor for the weight. And I guess it's just whatever analytically continuing.
Okay. Yeah. Okay. Cool. Thanks.
Igor? Or sorry, maybe Igor first, isn't it?
Oh, hi. I am very sorry for the naive question. It's just a beginner problem. I would like to know if it is possible to derive or at least motivate the large gauge transformations for non-abelian Young-Mills theories as one does in gravitation to arrive at the BMS group and find the super translations, such as the asymptotic analysis of bonding, Sachs, Meitner. Sorry if it's a very naive question.
No, I mean, are you asking whether there's an analogous story for the abelian gauge theory? Because yes, you have this, you have everything carries for this case too. I mean, you have also, subgluon theorem and the color memory. So it also works out for this case. Does that answer a question?
More or less. Let me just try to be a little precise and fast. I am sorry. In gravity, I can work out the asymptotic expansion like Bond and Sachs did. And then I will find out the super translations, which the people who were working particle physics, they did not care much about. They just care about the Poincare regular. So now we learn that we have the super translations, the soft modes in gravity. My question is, can we motivate the large gauge transformations only in the context of gauge theories living in Minkowski space without the need to talk about the BMS group, etc.? That's my question.
Yeah, of course. You don't need to. I mean, you don't need to care about Bondi, Metzner, and Zach to have a very rich story going on for gauge theories. I mean, historically, this is how the thing happened from gravity. This is the first instance where this thing were found, and actually Andy explained kind of yesterday why it was the case, because some reason the gauge case is more confusing than the gravity setting. It's easier to disregard these large gauge symmetries.
I understand.
But yeah, you don't need to have gravity to.
Okay, so thank you, and I am very sorry for the question. And just a little one more naive question. In the case of the memory effects, I have read a lot about the displacement memory effects, which are at a classical level. Is there any memory effect like the Aharonov-Bohm effect that we can measure a memory effect which is quantum mechanical in nature?
I mean, do you mean like in gravity, or do you mean in EM? Because in EM there is the example of it being a phase that you could measure with like the conducting examples that I guess.
Yes, because most memory effects I read about are like the Christodoulou ones. You have a displacement of test particles. But now I am thinking like a phase shift of a quantum particle.
Sure, I think the question is,
okay,
like, I think for the case of gravity, I want it to be classical because I just I mean, so in any sense where if you can have a reason to think that like a particle is dressed to the Wilson line and then like the metric changes something there, like go by all means go ahead for that. I think that it's a feature that for the E&M case, you're measuring it with maybe some sort of like phase type of thing because we already have those like superconducting qubits and like that condensed matter technology ready to go to measure it. For the case of gravity, I would want everything to be at least like classical from like at least only involving classical gravity, and then whether or not you measure it with some detector that like yeah, I mean, so in some sense like wait, so you have these things where it moves, you have a Sagnac effect for spin memory which causes a rotation. So if you have any gyroscope technology that measures something other like in a different way, then that would work. But yeah.
Okay, well, thank you very much for the patience principally.
Hi, yeah, thanks for the nice talk. I have a question about the conformally soft mode. So for spin 1, the conformally soft mode has 1,0 weight, and that primary operator has a level 1 null state. And for the spin 2, the conformally soft mode has weight 3/2, -1/2. And that has a level 2 null state.
Exactly.
So, yeah. So I guess my question is, maybe you have already mentioned that in your talk, but what's the general relation between a null state in a conformal multiplet and the soft theorem?
So it's there. Okay, I guess Andrea, do you think it's okay to talk about this? So there's some upcoming work. So it's going to be like. There's a nice structure, but I think it's actually like there's not as many as you would maybe hope in 2D. Like there's like basically another descendant on it turns you into these this thing that Andrea is going to introduce in the next talk. So I think it's upcoming work, and I don't want to like what you're saying is exactly what you would find for these soft theorem guys. But there's actually only a finite number of what I would like you would identify naturally as these guys. And their descendants do have an interpretation in terms of something that Andrea is going to mention. But basically, like you go from the primary down to the current, and then down to a generalized primary, like in a little descendancy relation. But I think I shouldn't talk too much about. But yeah, just because you mentioned exactly like that. Okay, all right. I think. Andrea, am I treading bad water? Good. Okay, I'm so sorry. I'm like, no, because like the thing is when someone says something exactly like you found, and then you don't say yes, we are looking at it, then I'm like, oh no, like oh, we don't know, but I don't want to be vague, and I don't want to, yeah. So Emilio is also on this. Do you want to add anything more, Andrea? Because I just flubbed, like I teased it and then I tried to avoid it.
Yeah, I'm gonna introduce this generalized conformal primaries later on, and
yeah,
we could have a discussion later.
Yeah. So maybe after Andy's talk, we can like say a little more about it.
But can I also ask just quickly, so what about in higher dimensions? Maybe it's related to Adam's question. So in higher D, you can still define this conformally soft mode as a mode with spin 1 or spin 2 and scaling dimension d/2, where d is the dimension of the celestial sphere.
Yep.
And that, of course, defines a perfectly fine conformal multiplet just from the CFT point of view. I guess, I mean, for spin, it might not be a unitary conformal multiplet, but it's a well-defined conformal multiplet. And is it true that that conformal multiplet has a level 1 or level 2 null state?
I assume so.
Higher D?
Mm-hmm. I did all the computations in 2D right now, and Emilio and Andrea were focusing on the higher D case. Did you want to say something, Andrea?
Yeah, maybe we discuss this after we introduce the generalized primaries.
All right.
A bit more.
Okay, yeah, I can. I'll wait. Yeah, thank you.
Great. Okay. So sorry if I derailed anything there. Thank you again, Laura, for a lovely
No,
talk.
thanks.
Obviously,
Thank
like
you.
all the discussion is because it was great. So.
Yeah, no, that's good. Yeah, and indeed, many more discussion to come after the next talk. So
I'll stop recording right now.
Thanks, Sabrina, for putting together this wonderful meeting. It has been a lot of fun so far, and I also look forward to more interesting discussions and teasers. So I'm going to continue the theme of studying celestial amplitudes and conformal primary wave functions, and I want to attack two different kind of questions. One is about underlying structures of scattering amplitudes, which relate gauge theory to gravity. And I will do this in the context of celestial amplitudes. And this is work with Eduardo Casali that came out in a paper from last July. And then in the second part of the talk, I want to ask the question, what can we learn from conformal primary wave functions? Are there some underlying structures? Are there even classical solutions that we can construct, and on top of which we can study scattering processes from the celestial perspective? And this is work done with Sabrina, and which came out just at the end of last year. So we heard already in the sessions from this morning or afternoon, depending on which time zone you're in, that there is a new basis for quantum field theory scattering amplitudes, which is pretty interesting. And it arises when replacing the plane wave states that we usually employ as the asymptotic states in scattering processes by conformal primary wave functions. And this is possible because the four-dimensional Lorentz group acts as the global conformal group on a celestial sphere, and we can recast the four-dimensional S matrix in terms of a two-dimensional correlation function. And we already heard in Thomas's lecture and also in Andy's and in Stephan's talk this morning that by studying these two-dimensional celestial correlators, we can gain constraints on the quantum gravity S matrix. We can also look for new insights and angles to study underlying fundamental structures in amplitudes, and this will be the context in which the work with Eduardo arises. Perhaps an even more daunting challenge than studying perturbative scattering amplitudes on flat space is to ask whether there's even an underlying holographic structure. So we like to do holography. Is there an underlying structure in asymptotically flat space? And the first question that one has to answer are what are the symmetries of the game, which was discussed already in Jeffrey's and in Andy's lecture and in Laura's talk this morning. And once we have figured out what all the symmetries are, we can ask, is there a dual field theory, a dual CFD living on the boundary of asymptotically flat space? And what are its properties? What are its building blocks? What are the constraints that we can get on quantum gravity? And perhaps the most ultimate goal would be to find a non-perturbative definition of quantum gravity in asymptotically flat spacetimes. The goal of my talk will be the following. So I want to exploit this Mellin map that came up already quite a few times, which allows us to map the basis of plane waves to a new basis called the conformal basis. And I want to exploit this map to study underlying structures that relate both amplitudes of different spin and classical solutions of different spin. And for the second part here, for the classical solutions, I need to explain this footnote here, which is that directly from the Mellin map, we only get Mellin transforms of plane waves, which do not transform as nice objects in the conformal, putative conformal field theory on the celestial sphere, but they're only gauge equivalent to these nice conformal primary wave functions up to pure diffeomorphisms or gauge transformations. So the purpose here will be to set up a framework which will help us explore bulk physics, which we might not otherwise see if we just think about Mellin transforms of perturbative amplitudes. So for both these directions, studying celestial amplitudes and classical solutions in a celestial language, the theme of the talk will be that of shifting spin on the celestial sphere. So those are the two parts of my talk. So fortunately, a lot of the material and the basics have been introduced by Laura and by Stephan, so I can just give a lightning review of the stuff we will need and the setup. And I will then revisit this relation between gauge theory and gravity amplitudes known as the double copy in a way that is suitable for discussing these fundamental properties of amplitudes in the celestial setting. This then ties into the next part, which is to study classical aspects of this double copy relation. And what we'll find is that there are different versions of a double copy that arise, which are operator valued statements. There's a wild double copy, and then there is a Cauchy double copy. And in studying these different relations between conformal primary wave functions, we will find exact solutions to Einstein's equations. And these solutions, they can be either analytic or they can have distributional support. And distributional support will then motivate the introduction of what we call generalized conformal primaries. And these will be related to boosted black holes, shock waves, and other interesting metrics. Okay, so let me start with the first part. So the points that we will need is that the four-dimensional Lorentz group acts as the two-dimensional global conformal group and allows us to express the four-dimensional S matrix in terms of a correlation function where operators are inserted at points W and W bar on the celestial sphere. And in this way, we can trade the labels, which on the left are the energy and the helicity of the particle in addition to the points on the celestial sphere. And those get mapped to the quantum numbers under the global conformal group, namely the conformal dimension delta and the spin J. In a bit more detail, what this map does is it takes momentum eigenstates, e to the ik dot x, to boost eigenstates, which are given by some normalization factor in delta, and then 1 over q dot x to delta, where q is a null vector, which points to the celestial sphere, to the point w, w bar, and x is the spacetime vector. So these are scalar wave functions, scalar conformal primary wave function in this new conformal basis. And we can construct spin 1 and spin 2 wave functions by multiplying with the appropriate polarization vector and tensor. And in this way, we can go from a basis of plane wave functions that have positive or finite energy to a new basis of wave functions, which are constrained to have complex dimension with real part being 1. So we can now study amplitudes in these two different kinds of bases, either in the momentum basis or in this new conformal basis. And depending on which basis you study scattering amplitudes, different properties will become manifest and others will become obscured. And this is the case for symmetries. Already Stephan mentioned that translation symmetry will be obscured in the conformal basis, and that will be important for what I'm gonna say next. And then we can study also hidden relations which might be obvious in one basis, but less so in another. Okay, so the hidden relations that I want to talk about, they are not so hidden anymore because they're known since a decade or so. There have been a lot of work since this paper by Bernd Carrasco and Johansson, and here's a review for those of you who are interested in all the references. For the purpose of this talk, all that I will need is summarized on this slide. So the slogan here is gravity is Yang-Mills squared. Now what does that mean? So if we start from an endpoint amplitude in Yang-Mills theory, we can write it in the following way. So there's a sum over graphs. There's 1 over the propagator. In blue up here are the color factors, which satisfy a Lie algebra Jacobi identity in the different channels S, T, and U. And then in red here are kinematic factors, which are functions of the momenta and of the polarization vectors. And then there's also this energy momentum conserving delta function, which will be very important. Now, at tree level, we can always find such numerators that satisfy a similar looking relation than this Jacobi relation, namely this one. And these will be color kinematics dual numerators. That's what they're called. So if you are in this situation, then what you can do is you can take these color factors and replace them by another set of kinematic numerators and find a different expression, which has now numerator squared. And it turns out that this new expression is precisely the expression for an n graviton amplitude. So somehow these graviton amplitudes magically appear if you square the numerators inside these integral expressions. Now, what's very important here and what I would like to stress is that there is this four-dimensional delta functions that are up front.
Andy has a hand raised if you're willing to take questions mid-talk.
Sure, I'd be happy to. Please interrupt me at any time.
I know this is, I guess, standard stuff, but I'm not that familiar with it. Is it unambiguous, this ratio n gamma over pi gamma? How do you decide what to put in n gamma and what to put in pi gamma? Is that because, yeah, that would affect when you're going down to the bottom line where you replace C gamma with n.
So I think it's unambiguous once you find these color kinematics dual numerators, but I'm not an expert in amplitude, so there might be some subtleties that I don't know.
I see.
Just the scalar propagators for the trivalent graphs. So you might ask, why don't we add some propagator pieces in Y gamma? And yeah, in principle, you could add that, but pi gammas are defined. The pi gammas, there's no freedom in there. The n gammas, there's a lot of freedom, because even if they obey the BCJ, the color kinematics duality, you can add, there is a lot of freedom to redefine them in such a way that they still obey that BCJ numerator. So they are not defined, they are not unique in any way, but the pi gammas are.
You mean individually?
But if the n gammas are unique, how do you always get the right answer for any choice of, and if they're not unique, how do you always get the right answer?
The right answer. And we can prove that by several ways, by doing factorization and checking other properties. You have to really check that you have the right answer. But they are not unique because there's a lot of freedom to redefine them. Even if you start with something that we know it's the right amplitude, you still have a lot of freedom to redefine them, and it's going to change the n gammas a lot, but it's not going to change the amplitude at the end of the day. Yeah, so it's literally gauge freedom in that sense.
Okay, thanks, Eduardo. Okay, so good. So we replace the color factors by another set of kinematic numerators, and then we end up with a gravity amplitude, starting from Yang-Mills theory. And so now the question that Eduardo and I asked was, how does this work for celestial amplitudes, or if? And one of the key points here is that in the momentum basis, the manipulation that lets us arrive at this squaring of Yang-Mills into gravity makes heavy use of energy momentum conservation. But on the other hand, when we compute celestial amplitudes and we integrate over all the energies and make use of this delta function and use it to integrate, and the manifest translation symmetry is lost, or at least obscured. So the question is there even a double copy for celestial amplitudes? On the other hand, if you believe that this is a fundamental property of amplitudes, it shouldn't matter in which basis you discuss it. And so for us, the question was, what is the correct prescription in order to arrive at the relation between celestial Yang-Mills and gravity amplitudes? So it turns out that the most natural generalization of dealing with this energy momentum conserving delta function is to leave them in an integral representation. And this has already been useful in other contexts, namely in the context of scattering on plane wave backgrounds and studying the double copy there. And so this was already introduced by Eduardo and collaborators. And we will make use here in order to make sense of the celestial version of the double copy. Now, in some sense, the celestial double copy will lie between the momentum basis double copy in flat space and the more general curved space double copy, because it needs a generalization of the usual double copy prescription. But on the other hand, it's much simpler than a generic curved space. So what we expect is that the celestial double copy prescription that we will arrive at will give hints on how to deal with a more general curved space double copy. So in order to talk about a celestial double copy, let me first talk about the usual momentum space double copy, but using this integral representation of the delta function. So here we have spin 1 and spin 2 plane waves. TAs are the color factors. And what we have to do is we have to compute the corresponding amplitudes for these wave functions. And I will do this in the simplest setting, namely that of 3-point amplitudes. So the contributions to the Young-Mills and the Graviton 3-point amplitudes are given by this expression in the wave functions. And when we plug them in and massage them a little bit, what we will find is the startling relation in red, which is that the Young-Mills integrand, if you square it, gives the gravitational integrand. And that happens after you strip off the product of the scalar wave functions. So that it's the integrand that squares after stripping off the wave functions. And what you have done to arrive at this nice relation is you integrated this gravitational expression a couple of times by parts. And so what you have made use of is that when you take partial derivatives and hit the scalar wave functions, you get a 1 factor of the momentum, and these momenta are spacetime independent. So that's what you used here. Now, let's try the most naive analog for celestial amplitudes, which starts with replacing the plane waves by these conformal wave functions given by phi. So remember, these are obtained as the Mellin integral of plane waves. And when we do that, there's another thing that we should incorporate, which is that we will mimic the way that partial derivatives act on the plane waves in the following way. When a partial derivative acts on these conformal wave functions, we will define the result in terms of what we call generalized celestial momentum capital K and multiplied by the scalar conformal wave function. So now let's look at the Mellin transforms of the amplitudes that I've shown on the previous slide. So these take a very similar form. The only thing that happened here was that the wave functions, the plane waves, got replaced by these conformal wave functions phi, and the momenta little k got replaced by these celestial momenta capital K. Unfortunately, it turns out that if you try to massage the gravity integrand by integration by parts, you do not arrive at the square of the Young-Mills integrand. And the reason for this failure of such a naive double copy prescription is that the celestial momenta are spacetime dependent. And moreover, when hit by a partial derivative, which happens when you try to integrate by parts, you get extra factors in the conformal dimension. So this is not enough. So what we propose to do instead is that you should start from this celestial momenta capital K, but now you should promote them to differential operators. And I call them curly K. And these curly K are defined to act on the wave functions phi as given in the box. So on the one hand, they just give back the celestial momentum, but on the other hand, they also carry the particle label. So in that sense, they're not equivalent to the usual partial derivatives because they keep track of that. Now it turns out, and in hindsight, this is not surprising, that these differential operators admit the following presentation. And if you were in Stephan's talk, also Thomas's lecture yesterday, you will recognize this as the translation generator of the Poincaré algebra, but now carrying the label of the ith particle. And so let me also point out that here this exponential with a derivative in delta is a dimension shifting operator. And so this relates to what Stephan was saying about shifting the dimensions in amplitudes and how gravity and G3 can be related. Okay, so now if we replace the celestial momenta by these curly K differential operators that act on scalar wave functions, the right-hand side is just the expression for the Young-Mills and for the gravity integrand that I wrote on the previous slide. So let me define this to be an operator valued numerator for Young-Mills acting on the scalar wave functions and an operator valued numerator for gravity acting on the scalar wave functions. Now the question is, after promoting the celestial momenta to these operators, does the squared Young-Mills numerator now correspond to the gravitational numerator as an operator statement? So on the one hand, if we let these differential operators act on the wave functions and then integrate by parts, we will get these extra terms that come with a dependence on the conformal dimension. This is what I mentioned before. But now, because in the Young-Mills numerator, we have squares of the same operator, we will also get a delta-dependent prefactor. And these delta-dependent prefactors are precisely the same for the ith particle. And so when the dust settles and you have integrated by parts enough so that you have massaged the gravity integrand into a nice expression, you will find that these extra terms in blue precisely cancel, and we get a match. And the match is that this operator-valued numerator in gravity, acting on the scalar wave functions, is precisely the same effect as taking the operator-valued Yang-Mills numerator, square it, and let that act on the wave functions. So we have shown here with our prescription that celestial 3 gluon amplitudes double copy into celestial 3 graviton amplitudes. Now we can go to 4 points. The new ingredients are now that we have these exchange diagrams with S, T, and U channels, and we also have the contact term. And in order to put this expression for the 4-point Yang-Mills amplitude into a nice form, we use a couple of properties of the propagator, denoted by G. And we will open up this contact term into contributions for the respective channels, S, T, and U. Now, once you've done that, your 4-point Yang-Mills amplitudes takes this very compact form. G is the propagator. These capital Phis with the labels S, T, and U are just combinations of the plane wave functions. In blue are the color factors. And in red are the kinematic numerators, which are already rather complicated expressions. And these expressions are the momenta and the polarization vectors. Now, the standard story, which I painted on the first slide, is that if you take these color factors and replace them by another set of these numerators, you get these numerators squared in the integrand. And it turns out that this whole expression here is nothing but the 4-point graviton amplitude. Now, what about the Mellin version of that? So we want to Mellin transform this 4 gluon amplitude and the 4 graviton amplitude and see if there's an underlying structure between the two. Okay, I think I already said that. Okay, so if we Mellin transform, again, what happens is that we replace the plane wave functions by these conformal wave functions, the momenta little k by the celestial momenta capital K. That in turn will modify these wave functions capital Phi, which was just a collection of plane waves before, will now be a collection of conformal wave functions. And the kinematic numerators, which depended on the little k's, now depend on the capital K's. So this is the expression that we get. That's the Mellin transform for gluon amplitude. And similarly to the 3-point case, this will not be enough to double copy. So instead, what we should do is the prescription that I gave you a few slides ago, which is to replace all the celestial momenta k by these operators curly k. That means that we have to replace these kinematic numerators by operator valued numerators, which gives us this expression. So this is still the same as the one before. But then what we want to do is we want to try to double copy and see if this gives the celestial 4 graviton amplitude. So what we do is we replace the color factors by another set of these operator valued numerators so that we have these operators squared in each of the channels. And then we have to do a little bit of work. We have to use some properties of Mellin amplitudes and how energies appear in the expressions. And at the end of the day, what we find is that this expression with the operator valued numerator squared in its channel does indeed give the Mellin transform of a 4 graviton amplitude. So what we have shown here is that the celestial 4 gluon amplitude double copies into the celestial 4 graviton amplitude. Maybe I should ask if there's any questions on this point before I go on. Okay, if not, okay, Andy raised the hand.
Yeah, is this, can you think of this as directly as a relationship between 2 gluon operators on the celestial sphere and 1 graviton operator?
Yeah, that's a very interesting question. I think what you're asking refers more to what Stephan or Thomas were doing by.
Yeah.
Right? So
right.
Morally, it sounds like there should be a relation, but so one question is, and this is related to that, which is whether you can see this double copy structure that arises here at the level of OPEs. And then I think that will make your question more clear.
Right.
I'm not sure how to answer this at this point, but it smells like there should be something. There should be something here. Here the operators are not really like gluon operators or anything. It's really just the momentum operator combined in a nice form. So like, let me go back. So these n's, these operator valued numerators n, they are just given by the expression that I wrote here, where the little k's are replaced by the curly k's. And in addition, which I have not shown here because this is the momentum space version, there's also dependence on both x and y. So because the celestial momenta were position dependent, unlike the momenta from the momentum basis. So these are rather complicated expressions that now are operator valued. So yeah, I don't see immediately a simple structure that answers your question. But it would be nice if there was.
Actually, could I comment on that?
Yeah.
I had been wondering about this for a while. It seems that the correct notion to think about is color kinematics duality instead of double copying two gluon operators into a graviton operator. You should think of mapping a gluon operator and the color index on that into a graviton operator. So one piece of evidence that sort of suggested this to me was that you could map the soft gluon operator, the Katz-Moody current, to the supertranslation current by sort of just, if you map the gluon, if you map a hard gluon operator to a hard graviton operator, and you take the soft limits on both sides, then that actually automatically maps a Katz-Moody current to a sort of supertranslation current. And then when you sort of compute the OPEs, they also sort of start matching. So there was this basic evidence, which at some point I'll have to try to take forward to the hard operators as well. But
I think, no, I mean, if anything, I would advocate that once Andrea gets to the stuff with the, like, even though it's at the wave function level, like she's doing some operator double copy stuff that probably could be turned into an amplitude statement. We haven't done that, but.
Yeah, so we have some wave function double copy statements, which might more directly relate to what you're saying and maybe to what Andy was asking than this double copy at the level of the amplitude. So maybe let's raise that question again in like 20 minutes or so. But yeah, that sounds very interesting. I think you're also giving a Gongsho talk on this, no?
I might mention it, but yeah, we'll see.
Okay, great. Looking forward to it. Okay, so okay, so 3 and 4 point celestial amplitudes double copy, provided that you replace the momenta by these operator valued expressions. Now, there's also a nice presentation for amplitudes, which fits with the theme that I promised, which is that of shifting spin. So if you start with a scalar amplitude and then act with a suitable operator valued numerator, you arrive at the Young-Mills amplitude. And then if you act with the same operator valued numerators to get the square, you get gravity. And so this all happens because you have this dimension shifting celestial momentum operator. And this dimension shifting operator in the amplitude leads to a relation between amplitudes of different spin. And that's very neat. Let me like display this for the n equals 3, the 3-point case once again. So we have these scalar amplitudes. And while before I have been talking about the numerator acting on this wave function inside this integral, you can actually take it outside. So we really have an operator valued numerator acting on this scalar amplitude, and then the square of it acting on the scalar amplitude to get gravity versus Young-Mills amplitudes. Now for more than 3 points, you should dress each analog of the scalar trivalent graphs with these operator valued numerators. And so you get this expression that has now 3 terms from the different channels, and there is some scalar amplitude in each of the channels given by expressions like so. And then the gravity and Young-Mills amplitude are related by having the color factors replaced by these operator valued numerators. Now, let me finish this part of the talk with a few comments and some summary. So we've explicitly shown this for 3 and 4 points in the previous slides, but it also extends to n points quite naturally. There's also some nice work by Eduardo and Datul Sharma about extracting the celestial version of the scattering equations and color kinematic dual numerators from the ambitwistor string. more of the amplitude twistor string in ADS. There are also recent results that have a similar flavor, where you have numerators that have an operator valued squaring relation. So this ties to the statement that we have here about these celestial momentum operators acting in the amplitudes. Then I mentioned before that because now you're sort of abstracting away from the basis and you have these operators acting on wave functions, this picture could be useful to study general curved space double copy. And then an obvious question is, well, what about other theories, not just Young-Mills and gravity, and also what happens beyond 3 level? And this is something that we're kind of thinking about. And there's one comment that I want to make which is that in n = 4 super Young-Mills, something very nice happens at loop level, which is tied to the niceness of loop amplitudes and even to all loop order in the momentum basis. So what happens here is that if you compute the all loop amplitude, the celestial all loop amplitude, what you can see is that there's a factorization, and you can actually describe it as an operator valued expression acting on the celestial 3-level amplitude. And so there's this operator, this loop operator, let's call it, and this is kind of related to the momentum shifting, the dimension shifting momentum operator curly K. So there's also a shift in the conformal dimension going on, and via the action of this operator, you can start from celestial 3-level amplitudes and go to the all loop celestial result. And this was done in work with Anand Gonzalez and Francisco Rojas last year. Okay, so that concludes the first part of my talk. Atul raised a hand.
I just wanted to ask, what is the appropriate spinor decomposition of these curly K operators in 4 dimensions? In that, should I take e to the d del, e to the partial delta and just take its square root? Or should I take like that, e to the partial h in one spinor and e to the partial h bar on the other spinor?
Yeah, it's kind of like that. So in the paper with Sabrina, we have a decomposition in a spinor basis, and we talk about a dimension, a spin shifting operator, which is related to the square of the momentum space operator. I did not put it in the slides because I wasn't going to talk about fermions, but maybe we can talk more about that either on Slack or in the discussion session.
Okay, I can check your paper. That's okay.
Yeah,
I'll read that.
Yeah.
Sabrina, you wanted to add something?
Oh no, I don't want to add anything. I just say check it out. Yeah, sorry.
All right. Any other question on this part? If not, then I will move on to more classical aspects of the celestial double copy. And the first thing to point out is that there is actually a straightforward classical analog of this operator valued double copy statement. So it is well known that if you take waves, electromagnetic and gravitational waves, that their curvatures satisfy an obvious squaring relation. So if you look at the Riemann tensor here and you strip off the scalar wave functions, then you see that it's the square of the field strength if you strip off the wave function. So for the Mellin transformed wave function, something even nicer happens, and this is as follows. So again, you can write down the curvatures. Now there is this delta dependent prefactor, which should ring a bell because this looks exactly like the prefactor that you get when you have 2 celestial momentum operators acting on wave functions. And indeed, using these celestial momentum operators, you can write down the field strength as a field strength operator acting on the scalar wave function, and the Riemann tensor as a curvature operator acting on the wave function. And then you don't have to do any stripping of the wave functions to get a nice squaring relation. You can just relate these curvature operators to each other. So, okay, that's very nice. But there's much more in store in this conformal basis. And that happens when we talk about conformal primary wave functions instead of just Mellin transforms of plane waves. And in order to do that, it is convenient if I introduce a nice tetrad for Minkowski space, which will make the expressions that we already know from Laura's talk, which will make them very compact, and it will display some properties immediately without doing any computations. So what I will do is I will start from these 3 null vectors, the reference vector Q that points towards W bar in the celestial sphere, and the polarization vectors constructed from derivatives with respect to the directions on the sphere. And then we also have the spacetime vector X, and I will use these 4 vectors to construct a null tetrad. So this null tetrad given by L, N, M, and M bar is such that you can write it Minkowski space in this way, and it satisfies the usual standard normalization conditions written down there. And the expressions for this null tetrad are given in this blue box. And so let me point out that this L here is like the celestial momentum that I introduced before for the case of delta being equal to 1. And then these other vectors are obtained by some shifted expressions also involving the spacetime vector x and the polarization vectors epsilon plus and epsilon minus. Now for the amplitudes people in the audience, let me point out something nice, which is that these null vectors m and m bar, they are actual natural space-time dependent polarization vectors. And the nice feature that they have is that they are invariant under the momentum space gauge ambiguity that arises when we shift epsilon to epsilon plus some number times q. So it might be useful to consider these polarization vectors in scattering amplitudes. Okay, so the nice property of this null tetrad is that under SL2Z transformations, these vectors transform covariantly. So lambda here is the Lorentz transformation, and then these two factors involving the W's and W bars, they arise from the Möbius transformation on the celestial sphere, and we can read off by using the general expression for an operator in a 2D CFT, which is said to have SL2Z conformal dimension delta and spin j, if it can be written in this form, if it satisfies this transformation property. And so from that, we read off that these null vectors L and N have 0 conformal dimension and spin, while the null vectors M and M bar have 0 dimension, but spin plus or minus 1. Okay, so most of the talk until now has used the Mellin transform of plane waves. So for the scalar case, this is a conformal primary with conformal dimension delta. But in the case of spin 1 and spin 2, these objects here do not transform as conformal primaries. And so if you want to study underlying structures in a celestial CFT, it would be better if we use objects that do transform nicely and serve as nice building blocks. And as we already learned in Laura's talk this morning, this can be obtained by adding terms that are pure gauge. So when we have done that, we arrive at conformal primary wave functions. So here I've just dropped this normalization factor for convenience. And then spin 1 and spin 2 conformal primary wave functions are given by a very simple expression if we use these null tetrad vectors m and m bar. So that's just that, and it's very compact. And maybe let me also point out that, yes, these conformal primary wave functions are gauge equivalent to the Mellin transform plane waves here, and you can even show this equivalence for finite deformations, eta plus this Mellin transform spin 2 guy. This is just the diffeomorphism, which is the difference between the primary wave functions of spin 2 and the Mellin transforms of spin 2. Okay, so now I've set up the stage for the rest of the talk, which is to discuss some underlying properties and relations of these conformal primary wave functions. So there's this famous thing called the Kerr-Schild double copy, which has received a lot of attention in recent years in understanding relations between exact nonlinear solutions of Einstein gravity. And what it does is it relates Kerr-Schild spacetimes to solutions of Maxwell's equations. So there exists a very nice gauge which lets us write a metric, depends on what kind of metric that is, but it lets us write Kerr-Schild spacetimes in this very simple form, which looks like it's a linearized solution, but actually one can show that one can bring exact solution to Einstein's equations like Schwarzschild black hole or Kerr black hole into this Kerr-Schild form. So phi here is a scalar that satisfies the wave equation, and this curly m here is called Kerr-Schild vector, and the property that it has is that it is null and geodesic with respect to both the flat metric and the Kerr-Schild metric G. And the famous property of metrics that can be put into this Kerr-Schild form is that it linearizes the Ricci tensor with mixed indices. So this is a very simple and compact expression, and this is the case for rather non-trivial nonlinear metrics. Okay, the statement now is that if G mu nu, this guy here, is a solution to Einstein's equations, then this object down here is a solution to Yang-Mills theory. And here the color factors are just constant, so we're really talking about a U1 sector, and so I will just be interested in the Maxwell solutions of this type. Now, it's not an accident that I chose this notation for the Kerr-Schild vector, because it turns out that conformal primary wave functions satisfy such a Kerr-Schild double copy. And the phi's here are really the conformal primary wave functions of conformal dimension delta. That's the scalar in the Kerr-Schild double copy. And the curly m here are just given by our null tetrad vectors m and m bar for spin plus or minus. And one can show that these null vectors, we already know that they are null, but one can also show that they are geodesic with respect to the Minkowski metric and the Kerr-Schild metric that is constructed by adding this spin 2 conformal primary wave function. Now, similarly to the flat metric, we can also write the Kerr-Schild metric in terms of a tetrad, but now we have to modify the flat one a little bit. And this is done by taking linear combinations of the m and m bar vectors, and also including the scalar wave function of dimension delta in the definition. Okay, so very nice. So now we have shown that there is some relation between spin 1 and spin 2 wave functions, but what does it imply now? So we can look at the curvatures, and let me tell you that the expressions are exactly the same as the ones that I showed you before for the Mellin transformed plane waves, except for this delta dependent prefactor that is different, and I will get back to that in a second. So now we can contract indices further and compute the Ricci tensor, and what we find is that it vanishes. So this shows that these conformal primary wave functions of spin 2, which have originally been constructed as solutions to linearized Einstein equations, are actually exact solution to Einstein's equations. Now, having found such a solution, such a pretty simple one, the question is, what type of solution is it? And for this, we compute the Newman-Penrose Weil scalar. And the only one that's non-vanishing is psi4, which is given by this contraction of the Weil tensor. The Weil tensor here is the same as the Riemann because we are in vacuum Einstein gravity. And then there is contractions with some of the null tetrad members. And because of this fact that there's only one vanishing Weil scalar, we can conclude that these conformal primary wave functions give rise to Einstein solution to Einstein's equations that are of Petrov type n. So then let me come back to this dimension-dependent prefactor in the curvatures and also in the Weil scalar. Now, what you immediately recognize is that these expressions vanish when delta equals to 1. And for the Weil scalar and the Riemann, they also vanish when delta equals to 0. And if you have been in Laura's talk, you will remember that these values of conformal dimension for the conformal primaries correspond precisely to the case where the spin 1 wave function becomes pure gauge and the spin 2 gauge function becomes a pure diffeomorphism. And for pure diffeomorphisms, the last Weil scalar that we computed will also be 0. And so this goes from being Petrov type n to Petrov type O, as expected for diffeomorphisms. Now, let me focus a bit more on the case of delta equals to 1. So as Laura explained, these primaries then correspond to the Goldstone modes of a spontaneously broken large gauge symmetry and BMS symmetry. And because of what I told you before, these also satisfy a Kerr-Schild double copy. And even you can write them in terms of potentials, and even the potentials satisfy some nice squaring relation when you strip off the scalar wave function. So in other words, BMS symmetry is a double copy of large gauge symmetry. And this statement was already made 2 years ago, but now we see that conformal primary wave functions are precisely in the gauge and precisely in the form so that this relation becomes manifest. Okay, so then one can compute charges associated to these Goldstone modes, which Laura discussed for spin 1 and spin 2. And now because of this double copy relation, it seems like the scalar with dimension 1 should also have a special place, even though there is no gauge symmetry. And this will be discussed in an upcoming paper where we'll find that there are a lot of subtleties when scalars are involved. And this is also related by a paper by Cambilia, Cuita, Misera, which discussed scalar charges. Okay, so then there are the conformally soft limit of conformal primary wave functions, which take a non-trivial form. Those are the ones that Laura discussed are the symplectic partners of the Goldstone modes, and they're related to memory. And they also satisfy a Kerr-Schild double copy. And from this, I can now define a conformally soft scalar, which has all the troublesome terms captures all the troublesome terms, which are step functions in x squared, logarithms, and distributional delta functions. The redshift for these solutions is again 0, and so we can again get exact solutions of wave functions. And now this is very interesting because these are associated to memory effects. So what type of solutions are there? So we can go ahead and compute the curvatures, and now the subtlety is that they are distribution valued. So we can take the Riemann and massage it into an expression that involves all our null tetrad members, and this will tell us that it's not clearly a type n solution. And the subtlety here is that at the location where this distribution has support, namely at q.x equals 0, the null tetrad diverges. But if we look just at the leading terms in the curvature, so if we're careful about what kind of space of test functions we use, and we write down the leading terms in the curvature, we get a Riemann that is singular as a distribution. So note there's this delta of x squared over x squared and delta of q.x over q.x. But if you're fine with such a singular distribution, then this is again of Petrov type n. So this is like a gravitational shockwave solution. Okay, so now since these distributional solutions seem important for memory effects, this makes us wonder whether we shouldn't relax the original definition of conformal primary wave functions. And this is what I'm going to do next. So we will call a wave function a generalized conformal primary scalar if it satisfies these transformation properties under SL2Z and has this specific conformal weight delta. And that's it. We don't impose anything else, no condition on the equations of motions. Okay, so now we have several options. So we can restrict to analytic wave functions, and then this will take the form of the ordinary conformal primary wave functions times an arbitrary function of x squared. So that's allowed. Or we allow for distributional wave functions. And now either the ordinary conformal primary wave function phi delta or this profile phi of f of x squared can be a distribution. So for example, if you take phi delta and you add an I epsilon prescription, but with a different sign, and then you take the difference and the limit, then you will arrive at delta of q.x. So that's one option. And in fact, this conformally soft scalar that I introduced before can be split into two terms, namely the one that has the step function and then the one that has this delta function in q.x. And you can show that these two wave functions separately satisfy the conditions for a generalized conformal primary. And that one that are underlined here in red will play a prominent role in the last bit of the talk. And I see Andy has raised his hand.
I missed something. Why do we want to think about things that don't solve the equations of motion?
Good. So you can either think of these objects solving equations of motions that are sourced, or you can think of them as off-shell quantities. And if you give me a few more slides, I will show you why these solutions are interesting. And there's two reasons why these expressions are interesting. Can you give me a few slides? And then if you still don't like it, you can say it. Okay, I assume the answer is yes. So I will move on and make the same statement for spin 1 and spin 2. So the only thing that we require is this transformation property under SL2Z. And then in addition, for gravity, of course, we want symmetry under exchange for the indices. And now we have more choices. So the first is when the 2D spin J is equal to the spin of the particle. So then we have these two solutions. And if we choose phi, these wave functions phi to be analytic, then we can reduce this to the ordinary conformal primary wave functions that we talked about before. But now we can also look at wave functions whose 2D spin is smaller than S. So in the case of the vector, we then have a solution that has spin 0. And for the metric, we have solutions that have 2D spin 1 or 0. And by introducing this null tetrad, it's clear because M, N, L, and M bar have definite spin. It's clear how you can construct this solution. And the one that I've underlined here in red, highlighted in red, is the one that will be important next. So let me just write this again. So let's now look at the solutions. Let's look at a simple case where almost all of these generalized wave functions are 0. And then we choose this generalized primary wave function 1 to take this form. So there's a q.x squared that multiplies this conformally soft scalar wave function, which is just given by log x squared times delta of q dot x. And so then we arrive at a generalized conformal primary metric that has spin j equals 0, and you can read off from the Q's that it has dimension -1. Now let's unpack this a little bit and see where this is sourced. So let's simplify this a bit and look at this specific reference direction. Then this expression will turn into a logarithm into Cartesian coordinates x and y, and will be restricted to this line in t minus z. And then massaging it a bit, we can see that this is actually sourced at a line. And then going back to generic reference direction, we find that the Klein-Gordon equation is actually sourced by a massless point particle. And that hopefully addresses Andy's question. So these solutions are interesting because they can be understood as arising from sources. And now thinking about massless point particles moving at the speed of light, there is an immediate metric that comes to mind that would be sourced by something like this. And this is the Eichelborg-Sechsel ultraboost. So the Eichelborg-Sechsel ultraboost takes this form. And lo and behold, this is nothing but a generalized conformal primary metric with spin 0 and dimension -1. Okay, great. So that's very nice. So that's one use of these generalized conformal primary wave functions. But that's not, okay. Sruti has raised her hand.
Yeah, sorry, this might be something that I just missed about the conformal primaries. But so when you're not talking about the generalized conformal primaries, just the usual ones, are you not allowed to talk about J less than S?
No, I mean, these would then correspond to, so here, if we would look at this, we would arrive at, so if you ask that they satisfy the box equation for the scalar in this case, you would arrive at the normal conformal primary wave function.
I mean, you're thinking maybe about a massive particle. Okay, I know you've done stuff with massive cases. So there are situations where you're projecting into like other
yeah, so in that case, yes.
Yeah. Okay. Okay, I see.
Yeah.
Okay,
so
thanks.
This is in a sense like, yeah, in spirit a bit like the massive case. And then the question is, what are these generalized conformal primaries that we introduce here? Kind of ad hoc, what are they useful for? And here we see that actually some physical interesting metrics take exactly that form. And there's another reason why they're interesting, and which I will come back to, and this relates also to the discussion that we just had before.
Okay, thank you.
Let me give you a few more examples here, maybe. So there's also d-dimensional generalization of the Eichelborg-Sechsel ultraboost, and this expression is a bit more complicated. And now instead of a log x squared, we have x squared to some power that involves the dimension. And one way to understand this function, so in principle, we can have any function f of x squared, but this function with this distribution can be understood from the combination of two shadow transforms of conformal primaries. And that is how this function x squared with some power would arise, and how this distribution would arise. And this is now a generalized conformal primary metric in celestial CFT d minus 2 with spin 0 and dimension -1. There's also something called the Drey-Toft planar shell, where this function f of x squared is now just given by x squared. And this is also a generalized conformal primary metric in d minus 2 CFT dimensions. Now, let me note maybe that the Eichelborg-Sechsel and the Drey-Toft chalk waves they are relevant for inserting supertranslation here. So there's another use of this this generalized conformal primary metrics. Then there is beam-like gravitational waves. So if you look at the metric surrounding a beam of null energy with a certain energy profile, it was shown in this reference here that you can get another solution to the equations of motion. And these have now a general function of x squared, and they encompass the previous cases. So this is now for 4 dimensions. There's another example, which is the metric surrounding a highly boosted spinning particle with mass m and spin s. And that's called the ultraboost Kerr-Giraton. And the metric is given by this expression, where A is given by this spin to mass ratio. And we have now this logarithm that's given by x squared minus this spin over mass ratio squared. And this kind of expression is also familiar from recent discussions of obtaining Kerr black holes from Schwarzschild black holes, via this complex shift called the Newman-Yanis shift. And here what we see is this ring singularity of Kerr at x squared equals a square. And these solutions would be expected to source spin memory. Now there's another example which was discussed by Andy and Sasha a few years ago in interpreting superrotation vacuum to vacuum transitions as the snapping of cosmic strings. So there's this metric that arises from finite superrotations that are glued across the light cone, where this is the Schwarzian. And then if we now allow ourselves to complexify the metric and we choose these finite conformal transformations zeta and zeta bar in such a way that the Schwarzians are given by these expressions, then the metric takes this form. There's a bunch of step functions, and then this H tilde 2 is what arose in Laura's talk, and this is nothing but the superrotation Goldstone mode. And then the difference between the G and the Minkowski metric is again a generalized conformal primary, but now with dimension 2 and spin 2 coming from the superrotation Goldstone. So these are a couple of physically interesting metrics which can be understood as generalized conformal primary metrics of different spins and conformal dimension on the SL2Z. Now I think I'm almost out of time, so let me summarize and comment on the second part of the talk, which was about classical aspects of the celestial double copy. So what I've shown you is that the conformal primary wave functions satisfy a Kerr-Schild double copy, and conformal primary metrics give rise to exact solutions of Einstein's equations of Petrov type N. And this encompasses as well the Goldstone modes of BMS and large gauge symmetry and their associated conformally soft memory modes. What I didn't talk about, but what is also true, is that these conformal primaries satisfy a Weil double copy. And this can be seen by decomposing the null tetrad into a spin frame. And that relates to what Atul was asking about before. Where you can see, well, maybe there's another point about this in 2 bullet points. So first, let me say that once you have decomposed the null tetrad in the spin frame, a natural question that arises is, what about massless fermions? We defined conformal primary wave functions for those and identified the conformally soft gravitino, which is the Goldstone mode for large SUSY. And then in an upcoming paper, we compute the charges associated to that. And these will be related, the water density for these symmetries are related to conformally soft Gaugino and Gravitino theorems. And this relates to what Stephan talked about this morning. Then now relating to the question of Atul, we also wrote down a spin shifting operator, which is related to the supersymmetry generator, but in such a way that it's not nilpotent. So we strip off the Grassmann variables, and then we can get an operator that allows us to go between wave functions of different spin in half-integer steps. And this sort of implements the theme of the talk that I outlined before, which is that of shifting spin on the celestial sphere. Then I defined generalized conformal primary metrics and showed that they are useful for relating to boosted black holes and shock waves and other shift states. And the second use, which came up in the discussion before, is that these generalized conformal primary metrics, they also appear in descendancy relations between conformal primaries. And that's also work to appear. Now, let me finish with some outlook. So perhaps the main goal of the celestial holography program is to gain insights into new bulk physics in asymptotically flat space. And what I try to convince you of is that the double copy, or here it's celestial analog, is a very powerful method that simplifies drastically the building blocks in this putative celestial CFD. And now the question is, what can this teach us about celestial CFD and about organizing scattering amplitudes and perhaps extracting exact backgrounds like the ones that I discussed about, on top of which we can scatter. So there has been a lot of work in recent years of extracting exact solutions to Einstein's equations from scattering amplitudes, and these are some examples. In particular, the last one here by Cristofoli talks about the examples that I mentioned before, namely Lachbuch-Sexel and the Kerr-Giraton, and he gets them from off-shell amplitudes with gravitons. The metrics that appear in these examples are generalized conformal primary metrics, and they are relevant for super translation here and for spin memory. And one question that arises is, shouldn't we also see some of this structure and some of this double copy behavior in the OPE coefficients of celestial amplitudes? And that maybe relates to Andy's question from obtaining operators in a squared form between gravity and gauge theory. And then last but not least, let me also mention again that there are some nice operator valued statements here, and they should hopefully inform us about how scattering amplitudes are related in curved space, hopefully via some nice double copy relation. And if we understand that, we can probably also use that to understand celestial holography on more non-trivial backgrounds. And that's it.
Thank you, Andrea. I think that was lovely, but I'm biased. Adam has a question.
Thanks. Yeah. Do you mind saying again what the claim was related to the snapping cosmic strings? Like who was the claim that you can write the symmetric with the delta equals 2 Goldstone?
Yeah, not the entire symmetric, because so this would only capture sort of one conformal primary. The symmetric would sort of need two. I mean, it's snapping cosmic strings. So here we just have things going in one direction. So I would think that we can only sort of capture half morally.
Okay.
And then there's a question about if you're happy with complexifying the metric or not.
Yeah.
Thanks.
Andy's next, I guess.
Just a quick follow-up on Adam's question. Was that expression you wrote down for the cosmic string metric as theta of x squared times the Goldstone boson? Was that only, that's just to leading order near scry? That's not an exact expression, is it?
This one is not an exact, so I mean, the same way that it's not the exact symmetric, right? But the other ones were exact all the way in the book. Oh, under.
And you pick a particular zeta so that you arrive at this. So everything here sort of collapses to this guy.
Is it this top one? That's the exact one?
This one?
Yeah.
I think this is the approximation there. This is the one where you were looking at basically just a gluing between, like on the light cone. And it's not exactly the symmetric. Okay.
Right, but this looks like Bondi coordinates. Do we have the exact form to all orders in 1 over r, or is this just the leading order? It's just the leading order, isn't it? In this gauge?
My impression is that you're matching onto, like, you wrote down this metric as if it were like extended into the bulk, but like it was as an approximation to the physical symmetric, and this was just like a gluing version of it across the light cone. Like in all the other cases except for this one, it's like exact everywhere. But I think that like we were just connecting it to this example of if you try to glue across the light cone. Atul had a question then, or Andy might still.
Yeah. So you've computed lots of nice backgrounds. Do you think celestial holography, in the sense of scattering amplitudes on top of a background, could be generalized to other curved asymptotically flat backgrounds? And if yes, do you think it requires the background itself to be one of these nice conformal primary sort of backgrounds?
I think ultimately we would like there to be sort of a real, a holographic duality, no matter what is in the middle, and once we understand how to deal with heavy states and so on. But here, this would be sort of the first, like if you don't know what to do with a black hole in the bulk, then this would be the first thing that you could do, because it also transforms nicely under SL2Z. So this is where I would go to study this question.
And then you could try to somehow extract like the f of x squared somehow from like a beam solution from the amplitude side. It might be fun to do.
Because recently we computed an MHV amplitude formula on radiative self-dual backgrounds.
Exactly, and these are the
yeah, at least a radiative background might be something on which you might expect holography to work.
Yeah, so all of our all of our deltas that are just the radiative solution. So before you go to the Gen CPWs, those should all be like definite self-duality properties. So any techniques where you have with MHV amplitudes are simpler on like self-dual backgrounds, you can say the same thing for like a heavy delta equals whatever radiative operator, and then like so normal CFT amplitudes.
I didn't mention this because I didn't talk about the Val double copy, but the conformal primary wave functions, they are all anti-self-dual, and the shadow wave functions, they're self-dual. And so this property you can then use to extract very easily what the Val double copy, which is a sort of spinor version of the Churchill double copy in some sense, is.
Did you try to solve the background couple linearized equation, scalar field, or any? Did you try to solve the background coupled scalar field or any other perturbation equation on these, on top of these? No.
We didn't do anything on top of it. No, we're happy to see it. There's a lot of other little.
This is like 4 weeks ago, so since then.
No, just asking. That's fine. Yeah. I was just curious.
But yeah, that's a very interesting question. Yeah, and yeah, maybe one of the motivations for looking at this.
Yeah. Does Andy have another question? I think.
Yeah. Could you just say what, maybe this is a hard question, but what would the picture be about if we just want to think of celestial conformal field theory as something defined by some collection of operators and OPEs and so on? What would it mean to have a double copy relation? What should we hope is true? And I guess this might be related to your statement about BMS being the square of large gauge symmetry. What is the?
Yeah.
What could the general statement be?
The general statement for what the double copy means, or what you can use it for?
Yeah. If you were just gonna describe it in terms of some property of the celestial conformal field theory, how would we describe?
Construction is how it comes to mind for me. But okay, so if I may suggest that I think that if we can combine our understanding with also, there's a recent paper yesterday by Campiglia and and so they definitely are looking at the same thing, and their example where they talk about the delta equal to, I guess, 0, whatever the super rotation one is, like, is also in a case that's like a subcase of ours. So they have a different interpretation of that, which might be more along the lines of like, what will this mean? Because like for us, we're like just happy to have these background solutions and there's all these cool properties. So I think somewhere between that and then also this Sugawara type construction, like that's where this is heading towards. But Andre, yeah.
Yeah. No, like the paper from, I guess today, or maybe for you yesterday, talked about the infinite tower of symmetries. While here we have the conformal primary wave function of arbitrary delta. It doesn't matter what it is. So this sort of it encapsulates the delta equals 1 case, which I looked at, showed in detail. But then any delta goes.
Yeah. So basically, like I think if you add their understanding to like then what we also have, like it's going to inform this picture in a fun way. So I'm excited to look in that.
Yeah. And also it should perhaps inform the question of, so for super rotation, we still have Goldstone modes, but for subleading, we don't. And so, there's still, you can write this square of spin 1 and spin 2, which is between Goldstone and non-Goldstone. So that might also inform the discussion of what happens for subleading soft theorems.
Right, because you're basically generating down in delta with your subleading soft theorem.
Yeah, because you have H0 and the spin 1 wave function with delta equals 0 is just the Churchill vector itself, because phi to the 0 is, phi 0 is 1. So maybe that will help with the interpretation.
Maybe I can just mention Maybe I can just mention the idea that I had somewhat more clearly. So my idea was that instead of double copy, we would have a color kinematics duality, in the sense that there will be a morphism of operator algebras. You take the full gluon, celestial gluon OPE, and there will be a map on the operators such that the OPE maps automatically to the gluon, maps the gluon OPE directly to the graviton OPE, in the sense that the OPE coefficients of the descendants would match. So what you could try to do the most naive thing, take gluons, take a hard gluon, map it to a graviton, delta to delta. Then that constrains your Kac-Moody current to map to the mixture of supertranslation currents. You take limit delta tending to 1 on both sides simultaneously. Consistent.
Map, what do you mean? What is your map?
That sounds like one gluon to one graviton. This is something two gluons.
This is no. I'm trying to instead of that you do color kinematics duality. You map one gluon to one graviton by mapping color to kinematics.
Right.
So the C replaced by N is the equivalent statement of what I said.
Yes. Because even if you compute amplitudes using gluon amplitudes, you'll still get half your kinematic factors already. So if you see, it shouldn't be that you map 2 gluons to one graviton, because they'll sort of square your kinematics as well. But, so what my suspicion is that the evidence that I sort of saw was at the first descendant level, where what you could do is you took the J-1 first Kac-Moody descendant and the J-1 current under this naive map from O to the graviton operator G, J-1 would map to what you call P naught minus 1 minus Z bar P minus 1 minus 1. Maybe I exchanged P naught minus 1 with P minus 1 minus 1. So there's a factor of Z bar which automatically appears, which you expect the graviton OP to contain. And then the OP coefficient of the first Kac-Moody descendant actually, so there are actually 2 Kac-Moody descendants at the first order because of color indices, and they have separate OP coefficients. And when you do this this mapping, those 2 OP coefficients combine to give the correct leading graviton descendant OP coefficient that is given in the paper by Shamik, BMS Symmetries of Celestial OP. So I just put this in my conclusions as a cryptic comment because I haven't managed to get the time to do anything beyond with this.
Yeah.
But this might be interesting if anyone wants to look at it.
No, it's interesting. I mean, the thing is like a statement like that isn't something that I don't think I could motivate a priori, but I know I can move between the wave functions with a differential operator or whatever I need to do to go between them. So we could give you a candidate operator and you could see if it's the same one as that you're seeing for your.
Yeah. Also, one comment is that the Cauchy-Galois copy actually doesn't take 2 gluons into one graviton. It multiplies by the Cauchy vector. So it's
no, but that's what he said.
Exactly. Yeah, that's the kind of thing I'm hoping for.
Yeah.
The subleading soft symmetry maps a gluon into a graviton. Could that be relevant?
That's like, as I said before, like A0 double copies with the Cauchy vector into H0, which is the shadow is related to a shadow stress tensor. So
under the map that I just under the naive map that I mentioned, the subleading soft gluon symmetry would map to the subleading soft graviton symmetry.
Yeah.
When you read the latest paper by Shamik and friends on the MHV gluon analysis, the subleading soft gluon symmetry has a J and a K, like it has 2 parts in it. So J plus Z bar K or something like that. And then if you map, then you have like the correct sort of mapping. J would map to P naught minus 1. And sorry, in that case, the subleading analog of P naught minus 1.
I think you can do by dimension counting.
Rotations,
Just if you keep track of the values of delta, you should see.
Yes, exactly. So you should be able to. So the most obvious test of this thing would be to sort of check if the OP coefficients match at a few more subleading orders and so on. So
yeah,
I'll do that at some point. Yeah.
Yeah, I mean, I guess is there a way to just look at interaction terms or some? I don't know, maybe yeah.
If you think about it in terms of celestial sphere, this relation should be similar to what you have where it comes from in string theory. That you have a closed string, so of 2 open strings. So on celestial sphere, okay, formally it that should translate to something which is called single value projection. And we have some geometric interpretation of the procedure, which you map graviton amplitudes and closed string amplitudes to open string amplitudes. But it should be very similar to what you have for the string theory somehow.
You mean about the amplitudes part, the perturbative part that I talked about, like doing this for strings?
Hmm?
You mean looking at the celestial double copy statement for strings, for string theory?
You know where it's coming from, string. So if you
yeah.
carry out this analogy to celestial sphere, it should be something similar.
Yeah.
You could take the old-fashioned KLT relations.
I think that's what he's talking about.
Yeah.
And
I think there was a paper even.
Replace the Mandel stamps with operator-valued Mandel stamps, and you should get something nice.
We don't have any way of thinking of, generally of thinking of a gluon as an open string, do we, in this picture?
I mean, except for, yeah.
Just historically?
We have this funny line on this, like the celestial sphere for 4 point, but that's not really anything with gluons, it's just schematic, so I don't.
I would think of it as a heterotic string more. Even the ambitwistor string suggests that, because there's no open ambitwistor string.
Open strings make a closed string, don't they? I mean, that was one of the original motivations for KLT, I thought.
Yeah. We want that.
But that doesn't work for ambitwistors, you're right.
Well, I think that was a lovely discussion after. This is exactly why we're so excited. It's the point of this meeting. So that's great. I might click stop now, and I would love to talk more.
Actually, there was another point. I was reading Shamik's paper, and he mentioned that in the Sugawara construction, it might so happen that the naive Sugawara construction, where just take two Katz-Moody currents and glue them together, only works as a stress tensor for the soft gluons and not for the hard gluons. But he said that if there might be a way to correct it by adding a subleading soft gluon contribution current contribution as well.
You know, that might be if you take delta goes to 0, you have like just like right m squared is the same.
Oh, so this
I don't know, maybe this is I'm just thinking of like naively like the.
Is this what Stephan did already? J0 times J2.
I think we should talk more like after and get to Andy's.
Yeah, there was a lot of interesting discussion there. So I hope when we get into the question session, we can have more questions on Andrea's talk and anything else. Okay, so thank you again. I am going to, it's fun to be talking here. And here's an outline of what I'm going to be talking about. Well, I'll start off since yesterday I just talked about the infrared triangle. I'll start off with 10-15 minutes just on my 2 cents on why celestial holography is interesting and what we should hope to do with it. And then I'm going to zoom in from general stuff to my latest paper from last week, which we're psyched about. And it's with, what happened here? Collaborators. Oh no. Collaborators, Alex Atansov, Adam Ball, Walker Melton, and Anna Reclario. It just appeared last week. And what I'll do then is I'll write down the toric Penrose for what we're calling Klein space, which is just split signature space-time in 4 dimensions. And then I'll show that if we study physics in that space, that the conformal primaries want to be discrete. And it's very appropriate because there was just a discussion about how this discrete set of values of conformal weights seems to be important and interesting. And then there'll be some general discussion. Okay, so this is the basic introduction part. So what is the idea of celestial holography? Well, the idea is that we start with an S matrix in Minkowski space, which is probably a complete set of observable quantities. And this is for asymptotically flat quantum gravity in asymptotically flat space, which is a very good approximation to the world we live in. And that its holographic dual is a conformal, what we call a celestial conformal field theory that lives on the celestial sphere out here at null infinity. And one reason, so this sphere, of course, is only a conformal sphere in quantum gravity because there's no natural way, there's no canonical way of going out to infinity. We can go out in different directions at different rates and different angles. So in quantum field theory, there can be a fixed round sphere at infinity, but in quantum gravity, the most we can hope that is well defined is a sphere, a conformal sphere. So the only thing that you could have that could live out there would be a conformal, consistently live out there would be a conformal field theory. And indeed, the Lorentz group, which is SL2C, is also the conformal group of the two-dimensional sphere. And so we're guaranteed that if we just rewrite, so there's no assumption here, it's just a fact that if we work hard enough, we can rewrite the S matrix in a different form in which we label incoming and outgoing states. The incoming states are in red, the outgoing ones in purple. We label them by the angles that they come in, that they exit or enter null infinity. And then they have additional labels, like whether they're ingoing or outgoing, if they have charges, what their energy is, so on. Though once we start talking about conformal field theory out here, it's much better, it's much more natural to characterize things by their boost weight rather than by their energy. And one of the nice things that happens is, I mean, we are used to in condensed matter systems in 2 dimensions that, and there are theorems to this effect with some assumptions like discrete spectrum and unitarity and so on. Once you have a global conformal group, you also get an emergent local conformal group. And an analog of that happens here. And what happens is that there's a subleading soft theorem, which tells you that this set of objects here also transforms under the local conformal group that's called super rotations. And so it looks even more like a conformal field theory. And now the price that you pay, but though in some ways it can look very nice, is that translations, which are manifest in the usual translation invariance, which is manifest in the usual plane wave description of scattering amplitudes, becomes inobvious. And in fact, what it does is if you have an insertion here, which we think of as being created by an operator that lives on the celestial sphere, whose boost weight is delta, a translation shifts that to another operator whose boost weight is delta plus 1. So things which were simple in one picture, as is usual in the case of a duality, things which are simple in one picture are complicated in another picture. Okay. Now, so if we want to find a holographic pair, the first thing we want to do, the first thing that was done in ADS-CFT, is to find the symmetries that both sides obey. And this thoughts about this began with de Boer and Solodukin almost 20 years ago, who looked at four-dimensional Minkowski space, and they said, let's describe it in this hyperbolic slicing. And then they say, aha, here's this Euclidean ADS3 here. And we can view all of four-dimensional Minkowski space as a kind of non-compact compactification over these hyperbolic slices. And since the compact, where we view the label of these slices, often taken to be tau, as an internal coordinate. But unlike in a real compactification, where the internal coordinate would be a compact, say on a circle, here it's a continuous parameter, tau, the label of the slices. And that means that the fields on these slices will be labeled by continuous rather than discrete parameters. So we get continua of operators in this picture, which live on these Euclidean ADS3 slices. But once we're on ADS3, we believe that we would think that there should be a Brown-Hanot type analysis would suggest that there should be a conformal field theory that lives on the boundary of these slices, which is the celestial sphere. Now, a sticking point in the de Boer and Solodukin analysis is that there seem to be two celestial spheres. So in order to describe physics in Minkowski space, we would need a map from one conformal field theory to another. But one of the things that we've learned in the last 5 years from the study of soft theorems, well, we've learned two things. One is we can actually prove that the conformal symmetry is there, not just conjecture it by analogy with ADS-CFT, but we also see that there's the conformal structure, the antipodal matching conditions lock the conformal structure of this past celestial sphere with that of the future celestial sphere. And so we really only have one conformal sphere, and we can view the in and the out operators as living on the same sphere. And then we're really cooking with gas, and we can really try to describe this thing as a conformal field theory, which lives on a sphere. And of course, there were many more people who contributed to this picture, including especially Barnick and Troussart, who had a whole different way of thinking about where this structure came from. Okay, now, why is this interesting? Why should we care about this? Well, first of all, there are a number of different motivations. One is that nobody thinks, as Juan emphasized in his talk on Monday, the very first evidence that that quantum gravity should be holographic came from black holes and the Bekenstein-Hawking area entropy law. And we have very beautiful, precise realizations of the holographic principle in anti-de Sitter space and the ADS-CFT correspondence, but we have yet to understand how it might work in the, fully understand how it might work in the asymptotically flat context. And indeed, also at 't Hooft and Susskind's original papers about the holographic principle were not in anti-de Sitter space. So this is something we'd really like to understand. And so there's a proposal on the table for how it might work. All these points are related. one of the things we've learned is that there are infinite numbers of symmetries in conservation laws which are at play in physics in asymptotically flat space. And we already know that, when a black hole evaporates, that there are we've long known that there are quantum correlations produced by energy conservation. So we know that the energy of the Hawking radiation exactly equals the energy loss of the black hole. And so that produces a small quantum correlation, which is nowhere near enough to have anything to do with the information problem. But when there are an infinite number of conservation laws, it could certainly be relevant. Also, there have been, from all kinds of different points of view, I guess as Nima put forth in his question at the strings conference in Princeton, that there should be the graviton 4-point scattering amplitude seems to be really constrained. And there's this nice formulas that come out of string theory, and they look like they might in some sense be the only formulas. How are we going to show that? Rudina made some progress on it, assuming some things. We'd like to make some really sharp statement about this. And it's clear that the symmetries that we make manifest in the celestial formulation of scattering in Minkowski space greatly constrain them. And so the hope is to make some progress in this new language on writing down the general form of the graviton 4-point scattering. Also along the way, we've a lot of connections, the shadow story and the light rate transforms, and a lot of connections to other double copy we just heard about. It seems to be connected in the Amplitudes program, connected to many other recent developments in mathematical physics. And finally, it's bottom up. We're learning new things about physics that is accessible to experiment. So there's been some predictions of a new kind of memory effect, which they might observe at LIGO. I talked yesterday also about the future, a prediction for the electron-ion collider that's going to be built for scattering in the Reggie limit. There's been various conversation with experimentalists and theorists about measuring electromagnetic memory and so on. So that's a further motivation. Now, so far, this subject has been mostly bottom up. So to explain what that means, that is the left-hand side, the scattering amplitudes are transformed that we compute however we wish using our traditional methods, have been transformed to define what the celestial amplitudes are. And we're not assuming anything about microphysics. So an example, one can imagine, and it's actually not very hard to imagine, a parallel universe in which Brown-Hanot discovered, well, of course, not a parallel universe. In this universe, Brown-Hanot discovered the asymptotic symmetries of ADS3 before it came out of string theory. We could imagine that, but it wasn't very highly developed, but one could imagine where string theory had been discovered several decades later, and we started with Brown-Hanot, and we'd say, hey, maybe quantum gravity on ADS3 is a conformal field theory. What would its properties be? And we would use consistency to work out the dictionary. We might have been able to learn, we could have learned something about black hole entropy that way. A lot of other things we could have learned, and we might have tried to generalize to higher dimensions. That's how the subject has proceeded so far. But I hope coming soon is also, you know, it's good to do bottom up and top down at the same time, is some sharper connection with string theory. There was an early observation by Stieberger and Taylor. I mean, after all, the idea of celestial conformal field theory is that you can compute the S matrix from a correlation function on the sphere. Those are certainly words that we've heard before, and in fact, decades before, when we use the string world sheet, correlation functions on the string world sheet, or on the CHY string or ambitwister string world sheet, give us space-time scattering amplitudes. And Stieberger and Taylor in an early paper made this precise in the limit of large conformal weights. Another thing which I haven't written here, but I think is really interesting is Juan has been suggesting that there should be some connection with the BFSS matrix model, which also is supposed to be a holographic formulation of scattering in flat space. That works at large n. It's in the infinite momentum frame where things are localized at a point on the celestial sphere. That's a very natural thing to think about from the point of view of celestial physics. An obstacle there is that BFSS runs into problems. If you try to lower the dimension from 10, you can kind of get down to 7, but then the dual is some strongly coupled theory. And we don't understand as well, you know, the celestial conformal field theory story is nicest in 4 space-time dimensions. It's not very well explored in higher dimensions, but it seems like there ought to be some nice way to make those things meet. But if we did have an intrinsic construction of a celestial conformal field theory, I should also add, Shuhong Shao, I don't know if he's on, has been saying that, you know, a free celestial conformal field theory can be thought of as a generalized free conformal field theory. But anyway, if we could get any kind of intrinsic construction of a celestial conformal field theory, that would be a really interesting major breakthrough. And now along the way, there's this kind of map from, you know, space bulk physics to boundary physics, and many things are encountered which are highly reminiscent of string theory. And part of the hope would be that there's a general sense that string theory is somehow the only completion, or things like string theory are the only completions of quantum gravity. And so we'd like to meet that idea working up from the bottom, which is what we're doing here, and maybe prove that a lot of structures that we encounter in string theory are more general. Okay, so there's a lot of things. We need to take some lessons from ADS-CFT holography, or in particular, we're talking here about 4 space-time dimensions, which would be sort of related to ADS3 holography in the slicing. There's a lot of things that are the same, but some things that are very different. one of the most salient things is that in ADS3 holography, or in all of ADS-CFT holography, there's no distinction between a bulk state and a boundary state. They're just the same thing. But in celestial holography, a state in the two-dimensional celestial conformal field theory, there is a state operator correspondence, is not exactly the same thing. It's related, it contains the same information, but it's not the same thing as a bulk state. So there's some things that are different about celestial conformal field theories and some things that are the same. So let me, okay, here's a kind of partial list. Both of them have actions of Verisaro. That justifies the word conformal field theory. We have current algebras often in usual conformal field theories. Here we get a, whenever you have a gauge symmetry in the bulk, you get a current algebra on the boundary, something that also happens in ADS-CFT. In usual conformal field theories, we like to talk about OPE singularities. We also have, those have now been beginning to be explored in celestial conformal field theories. And of course, they've already been discussed and studied at great length from the bulk point of view, where they're called collinear singularities. We have different kinds of representations. In ordinary conformal field theory, we, 99% of the literature, not all of it, but 99% of the literature talks about unitary discrete highest weight representations. Here we have different kinds of representations with possibly complex and continuous conformal weights. The notions of locality are different. Here we have unitarity of the space-time matrix, S matrix, which is not the same thing as unitarity in the two-dimensional CFT. We don't have unitarity in the two-dimensional CFT sense, but this might be related to some kind of sewing operation, two-dimensional conformal field theory. And I guess the biggest thing is that these celestial conformal field theories have a lot of extra symmetries in them. And it seems like too many. At first, when you look at this, you have something, you say you have some set of correlation functions which have the structure of those of an ordinary conformal field theory, and yet infinitely many more symmetries. You would think that there was no object that obeyed all these symmetries, and yet there are, because we can construct them. Also, of course, this is a new subject, whereas this is an old subject. Okay. So there's a rich structure here. A lot of different pieces of it are being discussed. A coherent overarching picture like we have in ADS-CFT hasn't emerged, and I certainly can't give you one. There's just a lot of different directions that people are exploring, which is both, I think, fun and healthy. And so I'm going to talk about one of them, which is the one I've most recently finished working on. Okay, so this is a paper which appeared last week on the archive. And one thing that's fun about it, let me mention here, is one of the things that we like to do in conformal field theories to study their properties is to study them on different Riemann surfaces. And so far, we've only had a way of studying them on the sphere. We had an algorithm for constructing the correlation functions on the sphere by doing Mellin transforms of space-time scattering amplitudes. And we didn't really have a good way of thinking about what the conformal field theory looks like on the torus. But now we're going to find that we get that by going to, the celestial sphere turns into a torus, as we're going to show, if we go from 3,1 to 2,2 signature. And we got tired of saying 2,2 signature space-time all the time. So I got a little history lesson from Nima, and Klein space seems to be a good word for it. It's also a catchy short name. So, okay, so why Klein space? Okay, so quantum field theory and quantum gravity are often defined by analytic continuation from 3,1 signature to 4,0 signature. And there are both good things and bad things about that. Of course, it's been an incredibly powerful tool. The first thing is that it gives us a very nice way of organizing all the I epsilon singularities in Feynman diagrams. We just go to Euclidean space, we compute, we analytically continue back, and all the I epsilons end up in the right place as far as for defining scattering amplitudes. Moreover, when we get to Euclidean space, all kinds of things are positive. Distances are positive, that's the first thing, but also we have reflection positivity, the masses are positive, and this observation is the starting point of the axiomatic quantum field theory program and all sorts of very powerful theorems about general quantum field theories with positive energy have been proven by analytic continuation to Euclidean space. So that's a great thing. Also, there are these non-perturbative instanton methods. So if you look at the classical theory in Euclidean space, that gives you saddle points for the path integral. And there have been all kinds of things which have been understood, Yang-Mills instantons, theta vacua, vacuum decay, all kinds of things have been understood non-perturbatively about quantum field theory, in addition to these kind of general axioms that were proven, all by resorting to Euclidean space. But then there's some things which are not so nice. One is that nothing can be on shell in Euclidean space because we can't have, we just can't put particles on shell in Euclidean space. And so when you use Euclidean methods to represent anything, you're resorted to doing sums of off-shell quantities, which you then analytically continued. And this has led, I think this is ultimately what is behind this, the huge number of Feynman diagrams that are needed to describe simple processes at higher orders in perturbation theory. And another related thing is that, 3-point functions of massless particles, which seem to be important, and in the celestial story, they seem to be coming, well, in celestial conformal field theory, in ordinary conformal field theories, the 3-point functions are the basis of everything. We think that if we know the operator product expansion of a nice rational conformal field theory, that's all the information about the theory. But the problem is that in celestial conformal field theory, these 3-point functions are related to scattering, if it's massless particles, scattering amplitudes of massless particles, which are degenerate in Minkowski space, and going to Euclidean space doesn't help. let's see where. Okay. Whoops. Okay. Now, an alternate approach. So there's pluses and minuses, mostly pluses. Euclidean space is good. But there's another good space, which is Klein space. And all kinds of people have talked about it over the years. Of course, Klein talked about it in the 19th century. Penrose really went to twistor space, of which Klein space is a kind of subset. And then, of course, the BCFW recursion relation, which starts with the 3-point amplitude, really has to be in Klein space because the 3-point amplitude doesn't exist in Minkowski space. So I think it's fair that most of the amplitudes program is either explicitly or implicitly playing out in Klein space. And the nice thing there is that in Klein space, particles can be on shell. That's one thing. And I think that is behind what has led to the truly dramatic simplifications of many constructions of scattering amplitudes, is that if you work in Klein space, you can be on shell, and so you don't get this huge, you aren't forced to consider this to sum over all sorts of canceling off shell processes. Now, and another part of the magic of Klein space is that the Lorentz group of Klein space factorizes into two very simple groups, SL2R left and SL2R right. Related fact is that the self-duality condition becomes real, so you can talk about self-dual field configurations. I guess there was Campiglia had a paper about this last night, which I haven't digested yet. But also very importantly for celestial physics is that there is a non-degenerate expression for the massless 3-point functions. So we can talk about them. So if we're going to take Klein space seriously as a kind of starting point for computing scattering amplitudes, whether we're doing celestial physics or not, we should understand what it is and what its boundary looks like. Now, this comes to my final motivation for studying Klein space, which is that in quantum gravity, the boundary is important. In fact, we think the boundary is everything. We'd like to say that the holographic dual lives at the boundary of the space. But the boundary of Euclidean space, the conformal boundary of Euclidean space, is just a point. So it's very hard to have a holographic dual which lives at a point. It's nice to have something with more structure. And so in contrast, Klein space has a very rich conformal boundary, which looks like a nice place to define a holographic dual. And the structure of that boundary, I believe, will provide constraints on what kind of holographic duals we can have. So the first question that I'm going to address in this talk is, what is the conformal boundary of Klein space? And the answer to this is surprised me in how rich it was, and it resonates with ideas of flat space holography and celestial conformal field theory. So what I'm going to do is I'm just going to tell you the answer, and then I'm going to derive it. Not that hard to derive. This is kind of a standard thing that we do for Minkowski space. So here is the toric Penrose diagram for Klein space. So first of all, we can write it. So here we have the triangle, and here we have the time-like direction, t, space-like direction, r. This is the origin, and null infinity is a single interval. There's only one null infinity. There isn't scri plus and scri minus. There's no past and future can be rotated into one another in Klein space. And over every point, the cool thing is that over every point at null infinity, there's a torus. So the celestial sphere has somehow turned into the celestial torus, and null infinity is a product of a null interval with a torus, which has a Lorentzian metric on it, since there are two time-like and two space-like dimensions. Now, there's one spatial, now since there's only one null infinity, we can't talk about an S matrix, right? An S matrix is scattering from a Hilbert space on scri minus to a Hilbert space on scri plus. Instead, we can only talk about an S vector. And what we're really discussing is an amplitude to send a bunch of stuff in and have it become nothing. And it has to become nothing because there's no place for it to go to. And it's possible for it to become nothing because we know that we can add up, since there isn't a positivity condition on the momenta. Any momentum, any null momentum, for example, can be using the Lorentz group, can be rotated into any other null momentum. In Minkowski space, future-directed null momentum cannot be boosted or rotated into a past-directed null momentum. But in Klein space, there's only one kind of null momentum, and they would be, if you like, you could characterize them by points on the celestial torus, together with an overall amplitude. So we can have positive and negative momenta in Klein space, and we can add them all up. It can add up to 0. And so we can have an amplitude where we send a bunch of stuff up in and get nothing. And that's the S vector that we compute. And there's a procedure, which I think Lionel Mason wrote a paper on years ago. People, I guess, understand it implicitly. There's a procedure for taking this S vector and dividing things into two categories, and a rotation which gets you the S matrix. But I won't be concerned about that. I'm not going to discuss what that procedure is. Now, the boundary of a boundary always has to be trivial. So it had better be the case that if we glue spatial infinity and time-like infinity to null infinity, we get a 3-sphere. And in fact, we can see how this happens in ordinary Minkowski space. It's a little complicated. Null infinity is a circle times past and future null infinity are both a circle times a null interval. But then we glue in future time-like infinity. Then future null infinity with resolved with future time-like infinity just becomes half of a 3-sphere. And we glue that at spatial infinity onto past null infinity resolved with past time-like infinity, and we get a 3-sphere. What happens here is a little different. So let me first talk about time-like infinity. So time-like infinity is 3-dimensional anti-de Sitter space mod Z. So 3-dimensional anti-de Sitter space, what I mean by that is we use, so it has, of course, one time-like dimension to it. If we take 3-dimensional anti-de Sitter space before we mod by Z, it's just a solid cylinder. It has a boundary which is S1 times the time, which is R. But now we do an identification which is periodic in time, where the period is just the natural period of anti-de Sitter space. I guess it's for a light ray to cross it. And we do an identification under periodic shifts in time. And so that turns the S1 cross R boundary into an S1 cross S1 boundary. Now, one of these S1 boundaries, in this case, the phi direction, is contractible. We contract it, we can pull it right in to the origin, whereas the time-like boundary, because we periodically identified, is non-contractible. So the topology of ADS3 mod Z is just a disk modulo, a disk times a circle. And so if we glue that in up here, one of the cycles of the celestial torus can be contracted over here, up here. Now when we get down to I0, we have it's also ADS3 mod Z. I'm going to show this in the next, in equations in the next pages, but with a minus sign, and we glue that in the opposite way, so that it's the other, here it was the space-like cycle of the celestial torus that becomes contractible. And here, down here, it's the time-like cycle of the celestial torus that becomes contractible. And so both of this, in the full geometry here, where we've put everything together, there's no non-contractible cycles, and the whole thing is just a 3-sphere. And indeed, this is the baby example in toric geometry, where you write S3 as a torus. Here I've tried to draw a torus with a red and a blue cycle. One of them becomes contractible at one end, and the other contractible at the other end. And this is the toric representation of a sphere as the torus fibered over the line. So that is the structure of infinity in Klein space. And indeed, this torus is fibered over this whole triangle here. And one cycle of it is contracted over here to 0. I guess it's the space-like cycle is contractible over here to 0. And down here on this line, the time-like cycle is contractible. So the whole toric Penrose diagram for Klein space is an exercise, elementary exercise in toric geometry, in which we write something which is topologically R4, except now, of course, we've got this Lorentzian structure added on top of it. We write Klein space as a toric fibration over the triangle. Now, what I've also illustrated here is lines of constant t squared minus r squared. So a light ray, starting from this point and at a fixed position on the torus, would just travel out to here. And if we fix the location on the torus, this region would be inaccessible to a space like, you can't get there with a space-like trajectory, with a time-like trajectory. And here is the region that you can get with a time-like trajectory. Of course, we can always go backwards in time by going onto the torus and winding around like this. So there's no causal separation as there is in Minkowski space. Maybe I should pause there if there are any questions. Understanding this picture is really the main point of the. Okay.
Andy, can I just ask, maybe this is related to this thing you're talking about, going from the S vector to the S matrix, but if I just sort of think pragmatically about 2,2 as just real lambdas and lambda tildes, if you're getting to this, I'll wait. But if I just think of them as real two vectors, if I have the sum of lambda tilde equals 0, I still have to have some plus signs and minus signs, right? I can't have, I can't do a separate SL2 rotations to put the top components of all the vectors to 1, or to something positive. So is there still some sort of some choice about what you think of as in and out?
I don't see from this geometry any definition but difference between in and out. I mean, if we have a momentum p.
Well, I'm just saying if you have a I think maybe the question would maybe I'll wait. Are you going to talk about like what the analog of the Mellon transform is here?
I mean, we talk about it in our paper, but I wasn't really going to.
Okay. Right.
I wasn't really going to talk about it here.
All right, fine. Maybe I'll come back to this question in discussion at some point. Then, yeah. I think that my question really comes up there because in the question of the transform in 3-1 signature we have a natural notion of whether energies are positive or not. And that positivity is sort of important in doing the transform from 0 to infinity. And I was wondering where that positivity goes in the transform to 2. I mean, there's a sort of very practical, dumb thing that you could do in practice that lets you get going. Anyway, yeah, let's sorry.
No, that's a good question. I think you're gonna feel at the end that I may have sidestepped it.
Okay. I'll wait. Thank you.
Okay, so let me write down some equations now. So I have two complex. We can just think of Klein space as two complex planes parameterized by Z and W with a relative minus sign. And then we go to polar coordinates in each of them. And we can write it like this. So we have one set of negative polar coordinates, that's the W's, and a periodic angle psi. And then we have ordinary on the positive component, ordinary polar coordinates. And then we use, what's interesting here is Q plus or minus R. And I guess I called it T on the previous transparency. Q plus or minus R, and we write that just aping things that we do in Minkowski space is a tangent of U and the tangent of V. And then after coordinate transformation, it ends up looking like this. And So we can, if we wish, if we just want to understand the conformal structure, we can cancel this term. But the boundaries here are at r equals 0, which is u equals v. That's this line here. Q equals 0, u equals minus v. And then v equals pi over 2, which is where this goes to 0. That's infinity. So that's this line here. So it's just the whole space lives in this diamond. And then we have a torus parameterized by psi and phi, which lives at every point on the diamond. And if we go out to null infinity, which is v equals pi over 2, this sine squared, both of these sine squareds become cosine squared, and they cancel the cosine squared down here. And so the metric up to the conformal factor of cosine squared v is just exactly minus d psi squared plus d phi squared, which is the metric on the Lorentzian celestial torus. And one can also see from this picture that the psi circle, which is the time-like circle, shrinks to 0 down here, and the phi circle shrinks to 0 here, but of course in such a way that the full space is smooth. So that's really all you have to do to derive this picture. Now, we'd like to foliate this with, as we did with Minkowski space, with slices of fixed distance from the origin, a hyperbola of fixed ZZ bar minus WW bar, which is just R squared minus Q squared. And these have, well, this one, if I make it positive, that gives me ADS3 mod Z, not just ADS3. So it's obvious that we would have gotten something like ADS3, but the mod Z, most of what I'm saying is pretty trivial. But the one thing that's not trivial is, or that confused me for a while, that doesn't mean it's not trivial, is that you actually get ADS3 mod Z. And to see that, you just do the standard coordinate transformation where we write Z and W in this way. And this only covers half of Klein space because we're assuming that W squared is greater than Z squared. And then we get a metric that looks like this, minus d tau squared plus tau squared ds3 squared, where ds3 squared is this metric. It's the metric on ADS3, except for the fact that psi is now periodically identified. Now, the fact that things are periodically identified, that we live on ADS3 mod Z, already there's a suggestion here, and I'm going to come back to that in a moment, that we're only allowed, if we start computing conformal primary wave functions on Klein space, we can't really have in the same way, because things are periodically identified, we expect the conformal weights to take some kind of discrete values. So it's going to become a discrete problem. The natural problem on Klein space is really one where things take discrete values rather than continuous values. But I'll come back to that in a more concrete way in a moment. Okay, so now, of course, this is, we can write out explicitly in Z and W coordinates, the L1 and L bar 1 we can write them out explicitly. And again, we see that if we, these are the generators of the Kleinian group, I guess we'd say. And if we go out to the boundaries, that is R to infinity or Q to infinity, the LNs act in the standard way that they would on the cylinder, okay? Which, of course, it's not the cylinder anymore, it's Lorentzian torus, because we've identified it. Now, by the way, if we take the Euclidean torus, it's important here that we have Lorentzian torus, because on the Euclidean torus, you know, we've broken, you know, there is no SL2R cross SL2R on, there's no action of the complex Mobius group that acts on the sphere or the plane. It doesn't act on the Euclidean torus, but it does act on the Lorentzian torus. If you have exactly the right identifications. And indeed, here is the finite Mobius action of, you know, of SL2R, which can act on either X plus or X minus. And that depends on having just the right identifications of X plus or X minus here. I haven't written it down, but psi and phi are both periodically identified, which means that X plus and X minus aren't quite separately identified. It's X plus goes to X plus. In this notation here, X plus goes to X plus plus pi, while X minus goes to X minus plus pi, or their difference. So the identifications are lattice and X plus, X minus space. Now, just as a side comment here, we're always, one of the things that has people been trying to understand about super rotations is how we're supposed to think about, if we're not in the global conformal subgroup, the super rotations on the celestial sphere in 3-1 signature all have singularities at some point. And although in ordinary conformal field theory, we understand how to think about those singularities and what to do with them, in the context of celestial conformal field theory, and we're doing something different with it, to computing space-time scattering amplitudes and so on, it's been less clear how to think about those singularities. Here in Klein space, if we go to the analog of super rotations, which would just amount to allowing the ends to take values other than 0 plus or minus 1, we don't have singularities. The diffeomorphisms of the circle to itself can be perfectly smooth, just like we don't have singularities in Lorentzian conformal field theory. Okay, so now in celestial conformal field theory, it's natural to scatter particles with conformal primary wave functions. And we're going to package that a little differently here, take into account that it's a torus rather than a sphere. So let's start from the beginning. We take, say, a massless scalar wave equation. Of course, we can separate that to a function of the ADS3 mod z slices times a function which depends on the coordinate in ADS3. You separate the wave equation with a separation constant k, which at this point is completely arbitrary. And of course, this is the Laplacian on ADS3 mod Z, which we can write in terms of the generators, which I presented on the previous slide. And now we can look for primary wave functions, which are annihilated by L1 or L1 bar, and are eigenstates of L0 or L0 bar, which are just psi and phi rotations. And it's just a few lines to show that these imply, what do? You commute these things. If it's annihilated by L1, you can use the commutation relations to write this term in terms of this term and a shift of this term. And we learn that the eigenvalue of L0 for a primary has to be 4h minus 1. And actually, there should be a bar here. H has to be equal to h bar for a scalar. There would be a shift, and we were considering a spinning field. And then the conformal primary wave functions take these very simple forms. And I should also add that it's natural to think about lowest weight solutions. Here, it's a convention, what we call how we organize our generators, and lowest weight solutions annihilated by L minus 1. We could also consider, as well as mixed ones, and we get more solutions that way. And we can also take all their descendants. Now, if we were doing ADS3, if we were just studying conformal field theory on a cylinder, we would have H minus H bar has to be in Z, so that as we move around the phi cylinder, the wave function comes back to itself. But now we've also got a identification in time, because we're not on ADS3, we're on ADS3 mod Z. So we also want to have H plus H bar in Z. And so, in fact, all the solutions of this type, these primary highest weight solutions and their descendants, are labeled by integer values of H. Well, these two conditions, H minus H bar and H plus H bar and Z, are equivalent to saying that H and H bar have to either both be integers or both be half integers. So the continuum, so you might think, if we were studying the ADS3 problem, looking for primaries in ADS3, we start out, as we do in ADS3 CFT, we start out with a scalar field of an arbitrary mass. We wouldn't find any normalizable solutions whose conformal weights for a typical irrational mass. We wouldn't find any conformal primary solutions corresponding to states in ADS3 mod Z where H plus H bar is in an integer. They would be equal to, and there's a formula that H is equal to, I think it's a half plus the square root of m squared plus a quarter in ADS3. We wouldn't find, and you could have that and then take descendants, you could get that shifted by integers. So you would never find any state that satisfied this condition. The nice thing here is, we used to think it was an annoying thing, but now it seems like a nice thing. The nice thing is we start out with a continuum of solutions of the wave equations labeled by arbitrary choices of this primary. This is the continuum of conformal primaries that we encounter in studying celestial conformal field theory on the sphere. So it chops that continuum down to a discretion. So when we're talking about the celestial sphere, we have an arbitrary conformal weight delta, which can be any complex number. We might want to restrict it for various reasons, but a priori it's any complex number. in addition to a position, Z and Z bar, on the conformal sphere. But here, these things are analogs of states that live on circles on the celestial torus. And we have an integer value conformal weight. H bar, of course, will be related to H, just will they be equal for a scalar? And then we'll have the level of the L-1 or L bar -1 descendant. So let me make some comments on that. So previous discussions of, and this is relevant to what Nima was asking me, is that the previous way we talked about scattering amplitudes, we were talking about involving point insertions of operators on the sphere. Now, in our paper, we consider analogous things, which are point insertions of operators on the torus. You can talk about a state that emerges at a point on the torus, but the more natural thing in this context, just as you could, if you're studying a CFT on a Lorentzian torus, you could insert an operator at a point. You could consider correlation functions of operators on the torus, but you could also talk about primary states, and that is the wave functions that the solutions of the wave equation that we have here. If we convolute them with field operators, they create primary states that circulate around the Lorentzian torus. And because they're circulating around the Lorentzian torus, not just propagating in time, they have to have quantized values of L0 plus L0 bar. Now, the discrete character of these kinds of primaries in Klein space resonates with other things that keep coming up in this discussion of celestial holography. People keep talking about these states. There is, of course, the what's called the unitary principal series, which is these states with conformal weights of 1 plus I lambda, which certainly don't obey this quantization condition. And they can be used to construct, they're a complete basis for normalizable wave functions. But the minute we act with a translation, we get off that series because we shift the conformal weight by a real integer. And so for many reasons, these integer valued conformal weights have been important. Indeed, as hopefully Anna and or Nima will discuss, if you look at scattering, so you can consider a scattering problem, you can, by analytic continuation, you can consider scattering states in 3,1 signature for arbitrary conformal weight, but you find that these have poles at negative even integer values of the total net conformal weight of the external states. And the poles encode all the information in the low energy Wilsonian effective action. And indeed, there's one pole for every term, and the sequence of pole encodes the information in the higher and higher dimension terms of Wilsonian effective action. So somehow you only, to get all the information about all these poles, you really need only consider scattering of objects with integer conformal weights. Now, moreover, as Stieberger and Taylor showed some time ago, translations shift the conformal weight by an integer. So these representations I've been discussing, actually, I've just been discussing SO2 representations, but they combine together into representations of the whole Poincare group, because the translations map one of these representations to another. And in fact, everything that I've written down, all the highest weight representations of a scalar field are just one giant representation of the Poincare group. Now, these integer weights have come up even more and even earlier when we start thinking about soft theorems, and there are poles in the OPEs at, if you take the conformal weight to be, the first one is the leading soft theorem. This one sits on the unitary principal series, but already for the subleading soft symmetry, there we find that it is actually related to a gluon or a graviton with a conformal weight 0, which can be written, and Andrea and Sabrina wrote a paper about this. Of course, they can be written as an integral over things on the unitary principal series, but the object you're interested in the end is the object with dimension 0. So it's clearly important to discuss these operators in the theory. And moreover, there's a whole infinite tower of symmetry. There's all gluons and gravitons with these values of conformal weights have poles in their operator product expansions. And this means that they generate soft symmetries, and they form an infinite tower of conformally soft currents. And these have been discussed there's a number of papers, but this one comes to mind, Banerjee, Ghosh, and Paul. I'm working with Alfredo Guevara and Mina Himwich and Monica Pate, working out in this form the symmetry algebra of these operators. And also for the positive conformal weights, these appear to be related to the Goldstone bosons, which are conjugate to these guys under the, I think it's probably conjugate using this generalization of the inner product that Andrea and Sabrina worked out. And so these integer weights are popping their heads up all over the place. And also we're looking at the partial wave expansion, and then we see there's this exchange of intermediate states. And when you expand, do a 2D conformal partial wave expansion of the 4-point function of massless scalar scattering, you get these conformal blocks associated with these states appearing in the partial wave, in the conformal block expansion of the 4-point function. So I guess I'll stop there, just say that we're reformulating the way we think about 4-dimensional Minkowski scattering, and it's leading to a lot of interesting new relations, and there's a lot of things we have to understand. So I will stop there.
Excellent, Andy. Thank you so much. Let's give a round of applause. And let's take any questions for Andy before we turn the, I guess, the recording off and go to a more informal discussion. Prahar?
Hi, Andy. So I don't know if you remember, at some point I mentioned to you that we can see these discrete real representations in 3,1 signature as well. So the way to do that is when you do the Mellin transform, you choose a contour in energy to integrate over, which is the standard, the naive choice is, of course, just integrating from 0 to infinity. And then you find by requiring that this is an invertible basis transform that you end up with the principal series representation. But if you instead choose to integrate like a circular contour in energy surrounding the origin, and this is not that crazy to do because we often do talk about analytical extensions of the S matrix in the complex plane. We need to study these things for crossing symmetry and whatnot. So if you take the amplitudes and do a Mellin transform, but now instead of integrating from 0 to infinity, you integrate in a complex contour around the origin in omega, then you'll find that requiring the same invertibility properties, you end up getting precisely discrete integer deltas on the real line. And then all of the properties that you kind of mentioned seem to hold, like delta obviously still goes to delta plus 1. That has nothing to do with the choice of contour. So the entire representation lies on the real line, and you never have to talk about the principal series at all. And another thing I usually like about this process is because you're integrating in a contour surrounding the origin, it doesn't care about the UV behavior of the theory. So you can UV complete the theory in whichever way you want. But you can still compute these sort of contour integrals because it's sort of effectively capturing some set of IR behaviors of the field. So my suspicion is that if we take your result that you've derived in 2,2 signature and do an analytic continuation back to 3,1, that what we'll find is that it's related, I think, to choosing this other Mellin contour to define a scattering amplitude. I'm not sure how that will show up, but there's this very similar structures. So,
well, it's certainly the case that it shows up in 3,1 signature. All those points that I mentioned at the end were things that had come up in discussion of 3,1 signature. What's interesting about 2,2 signature is that it's pushed on you more by the periodic structure of the torus. And that's very interesting what you say about doing the contour integral, but somehow there must be a little more than that, because we should be able to recover from the scattering amplitudes the terms in the Wilsonian effective action, and those come from infrared divergences near omega goes to 0. You at the end of the contour. So if we did some problem, well, maybe it appears in some other form.
No, it does appear because
your contour, because like you know that you have to go from 0 to infinity normally, right? So what are you doing to make that half real line a circle?
I'm not going from 0 to infinity.
No, I know, but why are you allowed to do that? Sorry.
I mean, you can choose. It's a basis transformation. The claim is that this is a allowed basis transformation. It also gives you completely invertible, a finite norm, all the properties that you want. The only difference is that I'm doing a contour integral in omega, and I get real delta instead of getting complex delta.
It's because you've decided to integrate around a circle. I think you need to motivate why you can do that contour change.
Well, it's a free world.
I'm not saying they're equal. I'm not saying that they're equal. I'm not saying that you can take the 0 to infinity contour and deform it. I'm just defining a totally new basis.
No, but is it a basis? That's what I'm saying.
Contour integral.
I'm only just worried about the fact that you're calling it a basis. Like, I think when I say it's a basis, it's equivalent.
I avoid the word basis because the basis for what? It's a question of what your norm is and what you want to calculate. Now, if it's a free world, you're certainly free to consider these operators and compute. The question is how we're going to get from them whether these operators enable us to study all the physics that we want to study. And the fact that we found that the terms in the Wilsonian effective action are all contained at the even negative integral poles on the real axis suggests that that the integral operators have an awful lot of information in them. However, I'm now confused or puzzled by your comment, because I know that the way that we thought of how these terms arose were from infrared divergences at the end of the Mellon transfer contour at omega goes to zero. So that's something that would.
But this is doing the same thing because you're doing a contour, so you're just picking up poles. So you pick out all the residues of all the actual nice poles that's sitting in the IR. And of course, I'm not just doing a contour, I'm multiplying by omega to the delta, the usual way. So omega to the delta, and then you do a contour integral. So by varying delta, you can pick out all types of residues, whatever you're interested in. By choosing delta to be, you can take delta to be 10,000, you can take it to be minus 10,000, and you can essentially pick out all the behaviors that you're interested in. In the IR. And another thing that this is nice is, but you can cut off delta. You can say, I'm only going to consider modes below 10,000, and that's essentially giving a UV cutoff to the theory. That's because all high, very, very high energy modes will no longer play a role when you're looking at just small deltas.
But I would view that as a plus, not a minus.
Yeah.
Because the fact that in quantum gravity, that things are soft in the UV enables us to start deforming contours around in a way that we couldn't in quantum field theory. So one would hope that in order to justify this procedure of just using integrals around the contours at small omega, that you would somehow need to use that.
Yeah. So my guess would be that in a quantum theory of gravity, if the behavior at infinity is sufficiently soft, then there's actually a procedure by which you can deform one contour to the other.
Yeah, that would be nice.
Yeah.
Yeah, be careful. Yeah. Be cool, but
yeah, but there you naturally get all, and in fact, one thing I showed was that there's only two choices you can make, which is very interesting. You can either choose the contour and get the real axis, or you can choose the Mellon transform and get the principal series axis. And there's really no other choice.
But that's R versus S1 though. Like that's what you're getting. Yeah.
No, if you require invertibility, and so the idea is that
in fact, you're transforming in a circle when you're doing that contour, right? You're getting all the integers because you're doing a circle. Yeah.
Yeah. Yeah. Anyway, and it's because it's a contour, and in 2,2 signature, of course, omega is, this, you can actually do a SL2 rotation. I suspect the fact that you have this compact torus and you're doing an integral in a circle on that torus is, when you analytically continue, will end up giving you in 3,1 signature will map to doing this sort of Mellon transform. It's not a Mellon transform, the contour integral.
I would almost think maybe the other way around. Like, so maybe like this is very naive and I have no reason to actually say this, but I would say that whatever we're doing in 3,1, which is normally this like 0 to infinity contour, might in his signature change into yours, and then that's why it works. I don't know. I mean, like I would think the other way around, because there you have a natural discrete this coming from the topology. But I don't know. I don't know. It's cool stuff.
Yeah, another thing, all of the, I mean, this isn't, the structure of infinity in Klein space, it seems like it should also imply, it's not limited to sort of the celestial holography program, because it seems like anything that's defined in 2,2 signature should be possible to to define as some problem where you're starting on the boundary of Klein space, and somehow there has to be this periodicity in all these formulas and the amplitudes programming, be able to be continued to be consistent with that.
I think so, yeah.
Pretty neat. I think Shuhong was the next person with his hand.
Hi, Andy. You might have mentioned this, but I missed the statement. So in 2-2 signature, is there a norm for this conformal primary wave function? And what forms a complete basis?
No, I didn't mention that. And I don't, I didn't mention that.
Okay.
And we actually avoided talking about norm in the paper. I guess when people do 2-2 scattering, there is some kind of analytic continuation which of the Klein-Gordon norm that would be used. Maybe you can think of the S matrix, the free S matrix, as some kind of norm. But also, as far as, I mean, I did make a comment, you know, complete basis is, the words complete basis don't mean anything without further qualification. So you could say complete basis for square normalizable wave functions, which is what the unitary principal series is.
Right.
But those things don't form a representation of the Poincare group, because the Poincare group, you know, they have delta goes, you know, 1 plus I lambda, and a translation shifts delta by a real integer. So that kind of complete basis, and indeed you can see that in momentum space. If you have something that falls off like 1 over omega, it, you know, that would be square normalizable, but if you act on it with the square of the Hamiltonian, it goes like 1. So that kind of complete basis is not exactly what we want in this subject. And we're certainly interested in you know, the things with negative integer conformal weights, which are not on that 1 plus I lambda line because they generate the symmetries. And so complete for what? So where I was referring to that was, what we really want is some set of scattering physics, some set of scattering amplitudes that from which we can reconstruct the whole theory.
Yeah.
So a conjecture would be that, I don't have any special evidence for this, but a conjecture would be that if we can compute the scattering amplitudes for all integer conformal weights, that is enough, that's everything we want to know. Real integer conformal weights, that's everything we want to know about the theory. And the reason that seems mildly plausible is that the 4-point function, that seems like enough to get us the 3-point and the 4-point functions. It gives us the poles in there, right? And then there's a question about the non-perturbative completion of that, which is yet another question. Yeah, so I didn't say anything, and we don't in our paper say anything about what a complete basis is, because we're not sure what the right notion of complete basis should be.
Is there anything that? Oh, sorry. Is there anything that computes the torus partition function of the CFT?
Great question. So yeah, when you look at a torus, you want to say partition function.
Right.
So now
then I would know the spectrum.
It's a Lorentzian torus.
Yes.
But that's not a big problem because you know what the Lorentzian torus really is a projection onto things with integer conformal weights, right? Things that can keep going around and around. So what would be a really interesting question is, let's call that the partition function, even if it's Lorentzian. What is the partition function of the celestial conformal field theory? Now, the other thing that we'd like to do, you'd like to do, is to vary the moduli of this torus.
Yeah, is that? But you get this rectangular torus from the Klein space directly, right? So what do you have to do?
Gives you a square torus.
Right.
But it seems that there are various things that we could do, like put a cosmic string in, a symmetric, or even a black hole, like a Kerr black hole. You know, there might be things which deform the parameter of the torus, and then that should be yeah. But it would be nice to know. It would be I mean this is all very new, but you know, it would be nice to know to what bulk question is the partition function of the celestial CFT an answer.
Right. But it seems that for the torus 0-point function, there's no particle in the bulk, right?
It should be, right? There should be whatever quantum fields live there, right?
The torus.
So there's no asymptotic state, right? At the very least.
Yeah, but that's fine. That's why it's a 0-point function, right? That's why it's like intervals.
The torus 0-point function, right? The torus 0-point function. There's no particles there, right?
Some vacuum.
Yeah.
Nope. So I like
a partition function all by itself. Well, I guess towards a partition in quantum field theory, the partition function all by itself would be the torus diagram. That would be the cosmological constant, right?
And there are also a lot of volume divergence. Perhaps we can subtract them.
Yeah. So we're much better off if we have a parameter that we can vary. So So we might yeah.
I see. Okay.
What was the topology ultimately of the boundary once you added the I plus and I naught to it? Like just to try to get a sense if the spectrum is.
It's S3.
Okay, good. Okay, so that should tell you something about the spectrum then being discrete, like I guess in Shu Hong's question. Cool. I also like your proposal for the definition of complete basis, because like I would say that when we're on the principal series, like I want to say the data on the principal series tells me enough to analytically continue. And so if you say the data on the poles is enough, that's perfect for me. Like I'd be happy. Okay, sorry. I should let Atul ask his question.
Okay, yeah, thank you.
Looks like Scott has a question. Is that?
Or Scott, yeah.
Hey, so now that you've started talking about the celestial torus, I feel like this question is fair game. So in ordinary CFT, we know that there's a complete set of CFT data that allows you that provides like a consistent formulation of the theory on any Riemann surface, namely the spectrum of scaling dimensions and spins and their OP coefficients. And furthermore, we know the complete set of consistency conditions that constrains that data, namely crossing of sphere 4-point functions and modular covariance of torus 1-point functions. Do you foresee any sort of structure like that in celestial CFT? And furthermore, like more specifically, is the can amplitudes on this celestial torus be built out of the same data of the theory on the celestial sphere?
Well, yeah. So I mean, I think we're a long way from the kind of, in ordinary unitary rational CFTs, it was sort of 20, 30 years between their, when they were first written down and when this theorems about complete data and so on were proven. I think we're a very long way from that, but sort of rigorous axiomatic formulations of celestial conformal field theories. But I think we're beginning to construct pieces, and indeed one of the things in our paper is a construction. There's sort of a state operator correspondence, and the ordinary kind of things that one talks about in the celestial sphere, those are like operator insertions. And now, of course, you can just stay on the sphere and do a state operator correspondence by ballooning those out, by conformal transforming that the point of the operator insertion out. But now that we have a celestial torus, we should be able to see the states of the theory running around that.
Yeah, exactly.
And those are the things that those are the primary, what we're talking about, what I was talking about at the last half of my talk were primary states, as opposed to the primary operators that people have talked about. And we give expressions for the transformations, which are analogs of expressions in ordinary conformal field theories between of the map from the operator state correspondence. So I mean, certainly we're hoping for something like that. And since you asked this question, I mean, one of the salient features of ordinary conformal field theory is that everything is determined by the 3-point function, almost.
Yeah.
And that's complicated to describe in celestial conformal field theory in 3-1 signatures, because for massless particles, the 3-point function is singular. But in Klein space, it looks better. And so, I'm hoping we can, make more progress on that.
Thanks.
Awesome.
So let me first start by thanking you for asking me to speak here. So it's a great meeting, and I think it is the first of this kind, right? Yeah. So yeah. So let me start. Okay, so in flat space holography, the dual field theory has to compute the asymmetrics. Now in flat space, the asymptotic symmetries are infinite dimensional, and they act on the asymmetrics, and the word identities for this are the soft theorems which were done by all these people here. Now the thing is that since so at this stage we don't know that what is the dual field theory in this case, but the thing is that since we have this infinite dimensional symmetry, so we can hope to solve for the asymmetrics in some simple examples, and that's exactly what we will do in this talk. So okay, so let me start with the here. So these things, so that we will do. So these things have been discussed in the earlier talks also, and the thing is that the way to do this is that first we do a machine transformation from the Fock space to the celestial sphere, and this is this integral transformation. So you have this field phi h bar z bar on the sphere, and then you have this creation or annihilation operator, so which is this omega z bar and sigma, and then you do this integral transformation that you integrate over omega, and then you have this prefactor which is omega to delta minus 1. Now the thing is that so this zz bar on which this field phi is defined, so that's the coordinates of the sphere. Now this phi h bar zz bar, so that's a primary operator with scaling dimensions h bar, and this h is just given by delta plus sigma by 2, and this h bar is delta minus sigma by 2. And the fact is that in 4 dimension, the Lorentz group is SL2C, which acts on the sphere as the group, as the global conformal group. And now this scaling dimension delta is some complex number, and we also treat this zz bar as independent complex numbers. So these things were actually discussed in other talks also. So now we can define the correlation function of the primaries, this phi h bar zz bar, as the Mason transform of the Fock space scattering amplitude. So this is given by this equation, and this S is the S matrix element. And now the thing is that if we make an SL2C transformation, then this correlation function transforms in the standard way. So if so, This is the expression, and this just note that this HH bar, those were the scaling dimension, and this sigma is the helicity of the massless particle. So now you can see that this is transforming just like the correlation function in a conformal field theory, and this SL2C transformation that maps this Zi to this thing, this AZI plus B by CZI plus D, where this ABCD, so that's an SL2C matrix. Now, so now let's talk about the word identities satisfied by these correlation functions. So we start with the subleading soft Graviton theorem on the celestial sphere, which has this particular form, and this S1 plus ZZ bar. So that's the subleading conformally soft Graviton, and this G plus delta ZZ bar is a positive helicity graviton with scaling dimension delta, and this S1 plus ZZ bar, so that's related to this G plus delta in this particular way. And we also note that this S1 plus ZZ bar, so it's a primary operator with scaling dimensions 1 and -1. Okay, so this. So now what we want to do is that we want to recast this thing, this subleading soft theorem in the form of a word identity, and that can be done. So in order to do it, what one can do is that you can actually expand this S1 plus ZZ bar in powers of Z bar. Now it stops at Z bar square, because if you look at this, the expression for the subleading soft Graviton, then you can see that the Z bar dependence is through this Z bar minus Z bar K square. So that's why it stops. If you expand this S1 plus ZZ bar in powers of Z bar, then it stops at Z bar square. So then by expanding this, so we get these three currents, which are just J1Z, J0Z, and J minus 1Z. Now, what one can do is that one can substitute this in the soft theorem, and then what one gets are these three word identities. So this for this J1Z, J0Z, and J minus 1Z. And now you can see that this has the standard form of a word identity, and this will be more clear if you see that these word identities, they are equivalent to the global cell-to-C bar transformations, which are of this form. So delta plus 1, which comes from j plus 1. So that has this form, this z bar square del bar plus 2h bar z bar acting on this phi. So which we know is the same thing as the action of L1 bar on phi. And how do you get this? So this is just the residue at the pole at, say, z equal to zk. So that's what we have here. So similarly, for J naught, we have this z bar del bar plus h bar, which is the action of L naught bar. And for J minus 1, we have this just this del bar acting on phi, which is the standard expression for L bar minus 1. So so now what one can do is that one can expand these JAs in terms of these modes, which we call this JAN, and they actually give rise to this local cell-to-C bar transformations of this form. So delta n plus 1, so acting on phi h bar is essentially just z to the power n, multiplying this this thing, which is this z bar square del bar plus 2h bar z bar acting on phi. And similarly, delta naught n acting on phi h bar z bar is z to the power n z bar del bar plus h bar acting on phi, and so on. Now these things are quite standard, but what is not so standard, what I will say is that these j's, they are, so I have written them just as function of z, but they have a dependence on z bar, in the sense that instead of expanding, suppose so this is an expansion of S1 plus z bar around z bar equal to zero, but I could have expanded around, say, z bar equal to some z bar naught, and then you will get a different set of j's. But the thing is that they are just similarity transformations of these j's by this L bar minus 1, which is this. So that's why the algebra which we have here, say, so this algebra is the standard one. So this is JAM computed at JBN is equal to A minus B into JA plus B by M plus N, and this AB is just Z0 and plus minus 1. And so this algebra will not depend on how I expand this thing. So this thing is actually, just keep this in mind, because this will be important. And this is the cell-to-C bar current algebra which we have here. Okay. Now the thing is that since we just said that we have this asymptotic symmetries, now in order to think of this SL2C bar current algebra as an asymptotic symmetry algebra, so it may be useful to think of this as a sub-algebra of the algebra of singular diffeomorphisms of the plane. Now, what kind of diffeomorphisms are they? So suppose we consider the diffeomorphisms of this form, where the z goes to z and this z bar goes to z bar plus az plus bz z bar plus cz into z bar square. So this form is, of course, so what we have done here is that if you just look at the global SL2C bar transformation, so that transformation will just be z going to z and z bar going to z bar plus some a plus bz bar plus c z bar square. And in that case, this ABC, they don't depend on z. But the thing is that once you make it local, you can make this A, B, and C dependent on Z. And the thing is that this algebra, so that requires that this A, B, and C should also have poles. So these are singular. And this is not a conformal transformation because this thing will mix Z bar with Z. Okay, so now we can choose a basis of vector fields which give rise to this diffeomorphism, and those are of this form. So this, I have this j minus 1n, which you can take, which has to be taken to is z to the power n minus z to the power n times d dz bar, and then of the same way. And then it's easy to see that the algebra of these vector fields is the same as the SL2C bar algebra which we had. Now this is the classical algebra, but the thing is that we'll see that this is the one which will be appearing in the tree level scattering amplitude, at least for the MHV. Okay. Yeah. So if is there any question? So I can take it now. Okay. So if there are not, yeah, is there any?
I think I encourage questions during this talk, but also we can save questions for the end if there's less pressing ones.
Okay, it's fine. Yeah, so I can just go ahead. Yeah. Yeah, so okay, so now what we want to do is that we want to find out the OPE between the this plus helicity, some bleeding soft graviton, and a primary phi. So this can be done. So this subleading soft graviton is this S plus, this is this S plus 1 ZZ bar. And what we do is that you take the soft theorem and you can expand this side in powers of Z minus Z1 and Z bar minus Z bar 1. So that's what we have done here, and what you get is this, and this J1 minus P, J0 minus P, and J minus 1 minus P. So those are some differential operators which have this form. So these can be easily obtained if you start from this thing, okay, from here. Okay. So this is, so I'm just trying to do this quite fast. because this is all quite standard from the two-dimensional conformal field theory point of view, actually. So this is a very standard thing. And the thing is that this we have also introduced this particular notation that this differential operator, this Carhartley J, so that acting on phi is some this J1, say for example, if you take the first one, so that gives you this Carly J J1 minus P acting on this is the correlation function of this J1 minus P acting on phi. So this is the so this JA minus P phi HH bar for P greater than equal to 1 are the SL2C bar current algebra descendants. Now these are the things in terms of which the OP will be written. So now you can also write this expansion. You can extract the OPE from this expansion, and that is just given by this. So now we have used this particular this descendants which were this, okay, just this one. So these things are actually important that we'll see, and this is given by this. So if you compute the OP between G plus and phi, and then if you take the subleading conformal soft limit, then what you should get back is this one actually, and this just follows from the fact that this S1 plus ZZ bar is just this limit delta going to 0 delta into G plus delta ZZ bar. Okay, so we'll come back to this when we do the OP between two gravitons. Okay. Now this equation is also saying that we have to have these relations, that this JAP acting on phi HH bar should be 0 for all P greater than equal to, huh?
I see a raised hand. Oh, sorry, I'm trying to moderate this. Lee, would you like to ask a question?
Yes, very quick question.
Yeah.
How do we know whether this is the complexification of general relativity or the real part?
Sorry, what was the question? Just
if you naturally write these operator algebras down,
yeah,
you haven't yet imposed an inner product. It's the complexification of the theory.
Complexification of the.
Well,
yeah.
if this is the theory of gravitons, it's a complexification.
Yeah, it is actually, yes. Because we treat the Z and Z bar as independent complex numbers.
Yes. So
is there any?
Oh yes, but maybe keep going in the discussion. I can raise some points about that. But let me ask one: Is your formulation chiral?
Chiral, yes, it is actually. So that we'll see.
Okay.
It is actually, because it does not treat the plus helicity and the minus helicity in the same way actually. So that's extremely clear actually. So that you will see.
Great. Okay. Thank you.
Yeah. So yeah. So that's an extremely interesting thing. Interesting in the sense that will be extremely clear actually. Yeah. So that's true. Yes. Yeah.
Yeah. It comes from twistor theory and Plebansky.
Yeah. Right. Yeah. So it is actually the same. Yeah. Yes. Yeah. absolutely, yeah. Yeah, so it will be clear actually, so that, yeah, so once I go to the scattering amplitude, it will be clear that in what sense it is actually. So is there any other question now?
I think that was it. I'm going to lower the hand.
Okay. Yeah, good. So I can now just go ahead with this thing. So this is the definition of this Cartenter algebra primary, and this follows from this equation. You can see that you don't have. So here it starts from p equals 1. This one starts also from p equals 1. This one from p equal to 1. So this, okay, just a minute. Yes. So that's the thing. And this, and on top of this, we also have this one, that this L1 bar phi HH bar. So J1 naught. So that's the zero mode of the algebra. And that's the L1 bar, which acting on phi is 0. So that's the definition of this field. And J naught naught phi HH bar is L0 bar. So that gives you just H bar. So we will actually use this thing. And these and they actually define the SL2C bar Cartenter algebra primary phi HH bar. Okay, so let me just now quickly go through this super translation word identity. And the thing is that, so that is the same as the Weinberg's soft Graviton theorem, and it is of this form. So you have this form, and then you have some pKs. So what do these pKs do? So this pK, they act on phi HH bar, and that shifts the scaling dimensions H and H bar by half and half. So it increases the dimension delta by 1, but it does not change the spin. Okay, and this S plus, so this S plus naught ZZ bar, so that's the leading conformally soft graviton, and it is just given by this, by taking delta to 1. Now just note that the subleading soft graviton was this when you take delta to 0, and this one is just going to delta to 1, and this is a primary with scaling dimension 3 half and minus half. Okay, so now actually we do the same thing. What we do is that if we want to recast this in the form of word identity, then we write this S plus naught ZZ bar as some P naught Z minus Z bar of P minus 1 Z, and this stops at this expansion stops at Z bar, because you can see that on the right hand side you have just Z bar. So that's the single power of Z bar. So that's at most you can have. And then with the we get the same kind of word identity. So you can just substitute this S plus naught ZZ bar, this expansion in the soft theorem, and then that gives you this. And then these these two word identities are equivalent to the global space-time translations of this form, and this you can see is just the residues at these poles. So we have just written here this phi h plus half, h bar plus half because of this pk here. Okay, and then we can do the same thing. What we can do is that you can define the modes of these coherence, and the thing is that they generate the super translations. So delta n comma 0 acting on this is just epsilon z to the power n plus 1 z bar times this. So this is just the global transformation, and you multiply this by z to the power n plus 1. And the thing is that this second one is also the same. You just multiply this by z to the power n plus 1. And we denote the modes by this PMA and PNA, where this M and N are integers, and A and B, so there this is 0 and minus 1. So these super translation, they actually form an abelian algebra. So now you have to do the same thing. So now I want to find out the OPE between this S naught plus ZZ bar and phi, this sum phi sum primary. And so I just so you can just expand the right hand side of this in powers of z minus z1 and z bar minus z bar 1, and what you get is this, and this where this p minus a comma z is 0 phi h bar, and p minus a minus 1 phi h bar are the super translation descendants. Okay, so this is the form. So this is this will come back to this later.
There's one more raised hand from Atul.
Yeah.
I've been confused about this formalism a bit, in that when your A and B indices only go from 0 and minus 1. So
yeah,
does that still generate all possible super translations?
No, they don't actually.
They won't, right?
So that, and yeah, so that's a very good question, and that's this chirality which actually Lee actually pointed it out. So you can see that all these are actually the plus helicity. So for that, you don't get all the super translations in that way. You just get this p minus pn comma z 0 and pn comma minus 1. So you don't get that. So if you want to get the rest, then you have to do the negative helicity. So you get basically half of what you should get here.
So are we saying that those should not be used as symmetries?
No. So I'll come to that actually. So I am focusing on a special class of scattering amplitudes for which you don't need them actually. So I'll just come to that actually. So I'll just 1 second. So these are just how does these yeah. So these the correlation functions of these descendants are of this form, and they are just obtained in the standard way. So let me skip this part. And then I have also the super translation primary here, which satisfies these things. And so they just come from here. Okay, so if you look at it, so the terms which could be there but they are not there, so you just set them to 0, and that's what these things are. Okay, So, and the good thing about this is that this SL2C bar Cartesian algebra and these super translation, they actually form a closed algebra, which is given by this. Okay, so this thing is actually, yeah, so you can check that these things hold. And I think the crucial point is this, that this SL2C bar and the super translations, they close. So they close in, and this is the. Okay, so now let me come to this actually. So the thing is that, so in this talk, so we'll be looking at this special class of this MHV amplitudes, and they have this particular area. So if you consider the tree level scattering amplitude in GR, then they have this property that if you take all plus or just one minus, then this amplitude is zero. So the first non-zero scattering amplitudes are of this form, where you have minus and the rest are plus. Now, so let's call these amplitudes as the MHP sector, and this has a following property that you don't have any negative helicity, soft graviton in the MHP sector. And the reason for this is that if you start with a MHP amplitude of this form, and if you make one negative helicity graviton soft, then due to the soft factorization, what you get is this. But we know that in GR, this amplitude is not there. So what you get is this. And this is just the statement that in this sector, you don't have the negative helicity soft graviton. So now, so I think so now we can see that this so the symmetries in the MHP sector is just this SL2C bar algebra and the super translations which are of this form, this Pn minus 1 and Pn comma z0, which form a closed algebra. And that's also the chirality which Lee was actually pointing out. So you can see that the plus and minus, they are not being treated in the same way, and that's how the symmetry algebra is actually just what you get from a positive helicity soft graviton. Now, so now let's explicitly check this for the OP, and so this part, yeah. So now let's look at the OP in the MHP sector. So if I take two outgoing plus helicity gravitons, then the OP, the first few terms actually, not well, I mean, you have infinite number of terms, But the thing is that I have written just 3 terms because those are the ones which I need. So they are of this form where this delta prime is just given by delta plus delta 1 so on. So so this expression, like the way it is written, it is quite standard. You can see this. I have this super translation descendants, but the thing is that this is not the final form of the OP, because these descendants which we have here so they are not all independent. So that's what we'll do now. Now to see this thing, what we can do is that we can take the subleading softly limit on this. So I can take this subleading soft limit on this G plus delta by sending delta to zero, and then I get that this one. Okay. Now the thing is that we know that this one, so this one is also given by this subleading soft theorem which we had, which I wrote down there. So it is just this, right? So it is of this form. So now what we have to do is that we will just claim, I mean, as we should, that these two expressions are the same. So if you now that this is what we get from the subleading soft Graviton theorem, and this is what we get by directly from the scattering amplitude, and so they have to be same, and that actually gives me these two equations, which are this 48 and 49. So you get this delta 1 minus 2 p minus 2 comma 0 acting on this G plus delta 1 minus 1 is this. So what you do is that you can see that the first terms are the same. This p minus 1 acting on this G plus delta 1 minus 1 gives you G plus delta 1. So this term matches with this one. But the thing is that this term will not match with this. So they have to be same. Similarly, if you look at the power of Z bar, the coefficient of Z bar minus Z bar 1, then these three terms, they have to be the same as this 2 times J naught 1, which is essentially what we have here. And you can write it in a more clear way. Now the thing is that these OPs, so they are true for all values of the scaling dimensions delta and delta 1. And the thing is that, so what you can do is that I can just shift it is just easier to shift this delta 1 by delta 1 plus 1, and that gives me these two. I have introduced this p minus 1 minus 1, which global time translation. And I also have this super translation, which is p minus 2 comma 0. So I get these two things, and so we can see that this must hold actually, and that is what we actually wanted to show, that these descendants which you get, they're not all independent, and that gives you this kind of decoupling relations. And the thing is that now if I use this equation, then I can write this OP in terms of this. So once I substitute, so I have this one, okay. So I substitute it here, which is this this. I just use this one, and what I, or this one, what I get, that is this. So this is in terms of the linearly independent descendants. And the thing is that what we can see is that the OP in this sector is actually written in terms of the descendants of the SL2C bar Carpenter algebra and the super translations, and which we said which was our claim because of the fact that we don't have any negative helicity soft graviton in this sector. And the thing is that the fact is that it is not just that they are written in terms of the SL2C bar and the super translation descendants, but the thing is that you can actually calculate these OP coefficients by defending that both sides transform in the same way under the SL2C bar Carpenter algebra and the super translations. And also the interesting point is that you can compute the leading OP coefficient, this B. This B is the beta function. So this B delta minus 1 comma delta minus 1 from the differential equations, which we'll now show. So these different. So the thing is that once you have these relations, so you can substitute this in and inside the image scattering amplitude, and then you can use the fact that the correlation function of these descendants are given by these expressions like this, or for the super translation descendants, and for the SL2C bar Carpenter algebra descendants, they're like this. So if you use them, you can write these differential equations, which are like this. Okay. So we have these differential equations, and the most interesting, yeah, so both are here, but this second one is the one which basically I think will well, I mean at least in principle you can solve for the scattering amplitude from this equation. And now let me just say that, yeah, so what we have done is that, so it is we have also explicitly checked, for example, this equation for in endpoint MHV, and this has been checked up to 5 points. So this we have done. And now so now let me add that since we know that if you go back to this equation, since these equations hold only for positive helicity gravitons. So for an endpoint amplitude, you get n minus 2 equations. So you get basically this, you have n minus 2 equations for n minus 2 for positive helicity gravitons. Okay. Yeah, so this is fine. So if there is any question at this point, then I think I can take that because I'm more or less done. Yeah, I'll just talk about these primary descendants. Okay, so now actually let's see if we can find out these equations. So far what we have done is that we have taken the scattering amplitude, and from there we got this OP, and then we showed that if this has to be consistent with the subleading soft limit, then these equations have to hold, and then we showed that they are the same as these the differential equations which we have. Now, one thing which I want to mention here is that you can see that you don't have any holomorphic factorization here, because you get both del z and del z bar, which is acting on this g plus. So in general, I think these equations are complicated, but well, I mean, whatever they are actually. So now let me just focus on one particular case, which I call this phi zz bar. So that has this form. Now the thing is that, so this equation we know. So this equation makes sense only if this phi zz bar. So that's a primary under the extended local symmetry algebra, which is this SL2C bar, current algebra, and the super translations. And now what we can do is that we can, I'll show that one can get this phi zz bar, in particular this coefficient, this delta minus 1, from this extended algebra. So for that I need some particular things. So this if you look at this particular state, this phi 1, which is this j1 minus 1 p minus 1 minus 1 g plus delta, so that has this scaling dimension h plus 3/2 and h bar minus half. Now, so one can easily check that the only other state which has the same scaling dimension is this state actually. So let's consider the linear combination of this form, where this C is some unknown coefficient. Now this phi 1 and phi 2, it turns out that both this phi 1 and phi 2, they are individually primaries under the Poincaré group. So that means this L1 phi I, L1 bar phi I, and P0 minus 1 and P minus 1 comma 0, they acting on phi I are 0. And that means that this C, so you can't get that from the global Poincaré symmetry, and for this we need the local symmetry algebra. Okay, so now so let's impose this condition, which is JAN phi equal to 0 for all n greater than equal to 1, and this is the definition of the SL2C bar algebra primary, which we had. So that is of this that is this one. Okay, so that's what we get. So that's what we use now. So we had this one, we saw that this is solved, this one is also solved, and also capital L1 also acting on that is 0. So we now have to go back to this one to see if this will solve this. Okay, and it turns out that if you use this, so you have to impose this JAN acting on phi is 0, and then the point is that you get J1N. You can easily show that this J1N and J0N they kill the state phi for all n greater than equal to 1. So we are left with this J minus 1N. And what one actually gets easily is that if you apply this J minus 1 on this phi, and if you demand that this kills the state phi, then you can get the C, and this is essentially, so you get this, which implies that C has to be minus delta minus 1, which is of course the answer which we had actually. So in the same way, so this is this comes out quite simply. But the thing is that the main point was that you need the local transformations, not the global symmetries will not play any role here in this case. And so now what we can do is that, oh sorry, I think I'm on, yeah, I just take 5 more minutes. I think I started here.
No worries.
Yeah, I can just take 5 minutes more.
Sure. No, this is interesting stuff. A lot of us are very interested in this, so we'd rather have you.
Yeah, so I'm almost done actually. So you can do the same thing and get this null state which you have, the second one. So all the things work out nicely, and yeah, so it is just that, so all these things they are very much similar to how we work with how we are used to working in the two-dimensional conformal field theories. It is just that this algebra, we also have this super translation. So that is the new thing which we have, and that's why we have all these states, decoupling of all these states. Okay. Now, actually, I just want to write down. So since, let me just go back to this. So if you go to the first slide, so we saw that this correlation functions of these phi's, so they are just making transformation of the S matrix in the in the standard Fock space. So the thing is that we have some differential equations for this side, the left hand side, and so since it's an invertible transformation, we should also have some differential equations for the Fock space scattering amplitude, and we write this in this way. So this so these A's are the creation or the annihilation operators depending on the sign of this epsilon. And the thing is that, so you can go to the Fock space by doing this substitution. So you just replace with the scaling dimension with minus omega I del omega I and all these things, and you just use this explicit form here. Suppose you look at this equation and do those replacements. So what you get for the Fock space is this one. So these are now the differential operators which are acting on the more standard for the more standard scattering amplitudes, and we have again n minus 2 such equations, because in an n point MHV amplitude, we have n-2 for positive helicity graviton. Okay. Now I just want to flash this thing that you can actually, so this was done by Shruti and me. So this was, so you can do the same thing for the gluons actually. And the thing is that you get some interesting equations for that. So if you look at this equation, so we have some notation here, which is this GA. Oh, this is actually GAH comma H bar. So yeah. So this A is the ACN Lie algebra index for the gluon, and this HH bar is the scaling dimension. And the thing is that you have these T's are the ACN Lie algebra generators, and this CA, so that is the quadratic Casimir in the adjoint representation. So we get these first two terms. So these first two terms, so they look like they are almost the same as the Nisnik-Zapolochikov equation, except that you have an HI which sits here, and this HI is crucial for this thing to make sense, but I'll not go into that. But the thing is that you also get an extra term, which is this one, and this comes from the subleading soft gluon theorem, and you need this so this extra factor of HI, and this third term which you get from the subleading soft gluon. So those are required because otherwise these equations will not make sense, because if everything works in the standard way as it works, like say for an like say for an WZ motel, then the problem is that this scaling dimensions of this G, this HH bar, so they will be fixed in terms of this CA, which is not the case here. So you get some of these things like this. So perhaps you can solve them, and it's the same thing. So for an n-point function, you get n-2 such equations corresponding to positive helicity gluons, and so it's just like the Graviton case, except that now this equation is more like more familiar to us, except this third term actually. Yeah, so I think I will stop here. So these are the some things which actually is quite confusing in this context, is that what is unitarity in this setting. And the thing is that the other point is that these subleading terms, so this OP, the existence of the OP means that the subleading terms in the collinear expansion, they have a universal structure determined by some symmetry algebra. And the thing is that, so it turns out like what I showed actually, I mean in some simple cases, that this universal structure together with the soft theorems, they should be extremely constraining. Now the thing is that, but in the standard way of doing the asymmetrics bootstrap, so these constraints are not part of that. So I think it will be quite useful if we know that how to combine these constraints with the more conventional way of doing the asymmetrics bootstrap. So I think, yeah, I'll stop here. Yeah, at the end. Yeah, so if you have any question, then you can ask.
Thank you very much. It's very interesting. I think Atul had his hand raised first, but he has to go, like, if it's quick, like, let's do Atul first and then go to
yeah. If you want, I can ask in the
no, go.
session.
No, go. No, we definitely have time for questions now. I think
I've just been confused about why do we have to use the subleading soft gluon symmetry in the gluon case, but never mention the sub-subleading soft symmetry in the graviton case?
Yeah, so that I did not mention, but we have actually checked this thing. So you don't get anything extra from the subleading soft graviton actually. So I can talk about it in some way, but the thing is that yeah, it is not in our ear, but we have checked it actually, that this decoupling equations which you have, so if you act on them with the global subleading transformation, then you get essentially what you should get by, instead of, suppose in this case, instead of taking the subleading conformal soft limit, if I take the subleading conformal soft limit, then I get something else, but it is not really independent of this, because the point is that if you act on this with the global subleading transformation and get that, so you don't get anything extra.
But can you at least get descendants of sub-subleadings of graviton symmetry in the OP, or are they not independent?
So it turns out that in the case of the graviton, it is not required actually. Yeah.
Okay.
Yeah, so that is what we found. So it is all in terms of this SL2C bar Cartesian algebra and the super translations.
Thanks.
Okay, Laurent then.
Okay. Hello. Thank you. It's very beautiful results. So I want to ask a question maybe about this bootstrap idea. So let's say if I summarize your results, and, the way I understand it is, tell me there's this infinite dimensional symmetry algebra, which is the semi-direct product of Carroll SL2C times Carroll, super translation, and then all the MHV amplitudes are intertwiners.
Yeah, yeah.
Like invariant vectors under this symmetry algebra. So now the natural question is, how much can you reverse the logic? That is, suppose you try to classify the sets of intertwiners of this algebra. Can you find something more than the MHV amplitude? That is
yeah. So
is the space
so that is an extremely interesting question. So the thing is that, well, so I think the other way of saying this is will be that if I look at these differential equations, so is there any other solution of them, like other than the MHV amplitude? Now the thing is that that we don't know, but it looks like that once you fix this SL2C bar and the super translation, it is hard to have something else, because the OPE and these primary descendants, they are completely fixed by this symmetry algebra. But the thing is that we don't, yeah, so yeah, I think that's an extremely interesting question, but yeah, probably, yeah, we have to do something more to see actually. If you
maybe this is why I was asking it the way I was asking, because here, if you think in terms of representation theory, what you're doing is looking at the tensor product of n, representation, and then trying to classify the invariant vectors, which is really classifying the space of intertwiner. In some sense, you don't have to use, you can, for the question of unicity, you can free yourself from the particular representation, like the differential representation you have. You can ask this question more abstractly, and maybe, using, and that could give you a very powerful tool, independently of the particular conformal representation you're using. Okay, so you don't.
Okay. Yeah, that's interesting, but we have not thought in that way.
Right, there would be kind of a bootstrap showing that the symmetry is powerful enough to completely determine the amplitude, which is.
It looks like actually, that once you fix this, perhaps this whatever you will get is just the MHV actually. But yeah, that requires a proof, but we don't have that. Yeah, but that I think the proof of that will be excellent actually. Yeah. So in some cases, yeah.
That's why this talk is so interesting, because you're setting up like these explicit examples where you see this wonderful like null state relations coming up, and then we can try to like look at it from different points of view and try to free ourselves from the like MHV starting point. So
yeah, so that's basically what we did. What I did in the second part actually, like second part in the sense actually. Yeah. Now, the thing is that this can be done. In fact, more can be done. We have actually more can be done in the sense that the full OPE can be constructed in this way. So you don't basically need anything else, just other than the fact that you have this SL2C bar correct algebra and the super translation. So yeah, but the thing is that but it requires more care actually. If I want to say that, this gives me this thing actually without anything else. Yeah.
Thank you so much for a lovely talk. I think that probably is enough questions for this part of like just following up on the talk, and I'm sure there's going to be a lively discussion afterwards. So I'm going to stop recording now,